this here, and then people won't know that I'm looking at it.
Yes. Yeah. Pretending to be.
I didn't have memorized things. Just not very good at memorizing.
And I imagine people in Paris seeing my recording. So that's also,
Yes, that's right. Welcome to the nth day of ICFP. But in good news, I have the next hour is something special that we'll see now. Okay. So it's my great pleasure to introduce Dan Lyon, who will be giving our keynote this morning. Dan's a familiar face in the ICFP community, but I'll still tell you a little bit about him. So he got his master's at OGI and PhD in Utrecht, I believe, working primarily with Eric Meyer.
and Simon PJ.
And Simon, yes, okay. And I don't know if you guys know the history of the Haskell community. Obviously, some of you I'm looking at here know it, lived it, but okay. But for the rest of us in the room, the OGI around that time period was really a special place in the history of Haskell, at least, and of course, therefore, the history of the entire ICFP community. I think Simon was there. There were, let's see, John Launchbury was there, Mark Jones was there, Tim Sheard was there. Like that, it was at that time when they were inventing the ST monad. So really a heady time to be part of that. Dan, of course, you guys, I'm sure, immediately think of COCA and algebraic effects. And that's a lot of what Dan works on. You guys know that stuff. But he's got a really wide-ranging career spanning a ton of different topics. So I made a little list here. So he's done a lot of work, important work with programming with replicated state, type inference, foreign functions. He's worked on the semantics of Node.js's asynchronous execution. And maybe to the younger researchers in the room, something that I think that's more impressive is Dan's commitment to building software. So you can see this in the way it sort of, if you look at his work and the way it kind of fuels the work, the ideas there, the building is very important. So beyond COCA and memalloc, which I think we'll hear a little bit about, he's built some of Haskell's core libraries like data.map. He's made a Madoko, which is a fast markdown document processing system. The first version of Parsec as well is also Dan's. So with that, let's welcome Dan to the stage.
Thank you, Robbie. That was awesome to hear. Memory lane. I also want to mention that my PhD was also with Deutsche Zwierstra, which sadly passed away a few years ago, but it was always a great inspiration to me. So today I'm going to talk about strong functional programming with effects and compiler-guided reference counting. And it's really about, not so much about the COCA language, but a bit more about like all the work that it has to do to be efficient. And it really started, many years ago. Thanks for mentioning data.map. In Haskell, there's the data.map library, and I was making, beautiful trees that are balanced, and you get this beautiful functional code. But when you look at it in a bit more detail, you see like, it's stacked linear to the depth of the tree because it's not a tail recursive call. And you see like, every time you go down a node, you allocate a new node, and probably you're going to have to clean up the old one. And in the end, we're quite a bit slower than if I would use like the red-black tree in C++, right? That's in place and iterative. So my machine, C++ is like 0.35 seconds, and Haskell takes 1.65. And it seems minor, but it's, in the end, if you want to do like real stuff, like people like where they care about these things, it's really hard to say, I'm going to use a beautiful functional programming language, right? And I think even the success of Rust in many ways is also because it has this predictable performance, right? So one thing I wanted to do in the past 6 years is like change this, right? Like it's kind of like I have these feverish dreams at night, about the functional programming dream, where like, the functional reach from the heavens, like Chris Okasaki's beautiful book, right, into like, the guy rolling in the mud, and you want to lift them up, right? So this is what I've been trying to do in the last, about 6 years, and I'm going to tell you what are the most important ingredients to reach that. And the setting is this Coca language that is like a kind of a K if you squint. And that's I've been working on it longer time, but recently it really improved a lot in that sense. And it's a beautiful language, strict evaluation like OCaml. Again, right, designed the language too with performance in mind in the end, right? Another big thing that Coca is known for is like effect typing. It's very important if you want to do good optimizations. You want to know what your functions are doing. It pioneered like algebraic effect handlers. And today what I'm talking more about will be like fully in-place programming, which it has. So if you don't know what it is, it'll come up. And much more other cool stuff like implicit parameters. We had a paper this year at PLDI. Please, if you like overloading and implicit parameters, take a look. So to make Coca run well, we needed to invent a few really important things. So the first one is, like if you have algebraic effect handlers, normally people capture continuations on a stack and stuff, but we really wanted to compile it down to like a pure lambda calculus. So this was work with the wonderful Ningning Xie, was an intern at the time in 2021 or something. So we compiled down algebraic effect handlers down to pure, strict lambda calculus. So now all our effects are like nicely contained. And now we have a beautiful small core language. And then, this is the most important part, we don't use a special runtime system or a garbage collector or something. No, we're going to compile the pure lambda calculus with reference counting instructions. And that's called Perseus. I think it's called precise, I forgot, reference counting with reuse, I think, yeah. But it's kind of compiler-guided reference counting, and in this talk I will talk about it more. Lots of cool, this actually started with Leonardo Nomura and Sebastian Ulrich, who were at the time at MSR as well, for Lean. So Lean also uses this reference counting. And the nice thing is, now you do reference counting, in the end you get a pure C program that you generate, just using standard malloc and free. And you don't need a garbage collector anymore, or root scanning, or fancy runtime systems, just C. So Coca, for example, can just run in the browser because it's just C, right? I can like compile with mscripten or something, and it's really liberating to kind of try to optimize performance. And then as part of that, there's like a side quest. I also created a allocator for malloc and free, especially for like small allocations, like in Coca and Lean. And I'm going to show that too in this talk, because it's very important as part of the whole package, right? Simon Peyton-Jones always said, like, a compiler, there's no silver bullet, right? You need lots of bullets in your gun. So this is, you need all these things to work together. Simon Peyton-Jones also said, never show an overview in your talk, because, who cares, right? Like, but it's going to be 5 parts, and hopefully you'll enjoy them all, right? So you know at least what's coming up. So first, I think I do a little introduction to Coca, but just little, because I really want to talk more about all the backend stuff. But you at least get a flavor of what it's about. So there's this site where you can go and you can read about it and you can install it. And a nice way to install it is actually use VS Code. So if you go, to like extensions and you type Coca, you'll get the Coca language. And if you press install there, it will install everything for you, and it will just hopefully work. And then you get like a directory with lots of examples, so you can start playing, right? And I made a file here that's called Keynote module, and you see some Coca code here. And I thought it's kind of nice. Tim Whiting did a lot of work on making it nice in VS Code, right? So you can like hover, and you can see like, oh, example 1 is a unit to a string function. And if you do inc, well, it's a int to int function, and you can even run it. Like here we show the sum of a list that I map the increment function over. And I can, run debug, for example, and then it'll compile it and run it, and then it says it's 9, if you believe it. And it's so it's quite nice that way. Another cool thing I think to say is that it has static overloading in there. So the ink here, if you looked here, it was actually qualified name, like it's in the integer module ink function into int. And of course, there's also a float ink, or here the show function here. Well, the show for integers, right? It's the int show function from int to string. And unlike Haskell type classes, this is like static overloading. Looks at the local scope and picks the right candidate if it's there. So there's lots of cool stuff in there to make it easier to program with, because the core is like really small. We're going for like a solid semantic core. We have lots of like nice syntax to make things nicer. So this is something we use a lot, like the little dot, to kind of pass it as a first argument. So this program here is the same as the one here. You say, oh, make a list, map an increment function, take the sum, and then show it, right? And an interesting thing about Coca that I already mentioned is that it infers effects. So instead of here we see a function where I print the final result, and now it's like a unit-to-unit function. But you see there's like a third thing there. Oh, it says it has the console effect, because the print line writes to the console, and that's anything you do with the side effect will always pop up as an explicit effect type in your signatures, so you know what's going on. Another thing, there's no built-in control flow otherwise than that. So a lot of the things we do are done with functions. So here, for example, we repeat 10 times calling this function. So it's a parameterless function, a lambda, which just prints high, right? So if I run it, we'll get 10 highs. If you believe me, there are a lot of highs. We want to write it usually a little nicer, so we have trailing lambdas. You can put your lambdas outside of the parentheses, like following the function calls. But no, I have no time. But later, ask me, why do I have parentheses, and why don't I use like curried notation, right? And think about effects, and then maybe you'll answer for me already. But yeah, you can have trailing lambdas. So you can have, lambdas behind the last part. And then you can leave out, like if there's no arguments, you can leave them out. So you can just, write braces. Now it's almost a control statement. Well, if you indent, that's braces, right? So you can actually write it like this. And now that's just syntactical transformations. It doesn't change anything about the core, but now you make functions. It's much more easy to use them as like control flow statements, right? And if you look here, for example, for the while, it's just a function. So I can look at it, right? It's just a function. It takes a predicate and an action and keeps executing that. But you can write it in a kind of a really nice way, right? So here's the body of the while, which is really nice. And then you see the predicate. Oh, I use these braces, right, for anonymous lambda. And that's nice too, because in C you have parentheses, but it makes no sense, because anything between parentheses you evaluate upfront once, but between the braces is suspenders, right? And I think you don't know how often you're going to evaluate it, right? For a while loop, you're going to evaluate it maybe many times, right? So I think we like that it's braces for the predicate here. I think this is the most important thing I wanted to say about Coca. But later I'll show a few more programs. I thought one cool thing, I think, that why I like effect type so much is that it gives you a really good idea about what your program is doing, right? So if people ask me, well, what is an effect? I always say, well, if you create a semantic function of your program, then the type of that, right? That would be the effect if it has a different type than the plain one, right? So if you have total functions, there's like no effect at all. It will always terminate. It will never like diverge. The mathematical function that models such thing is just int to int in this case, right? Integers to integers. But if you can raise an exception, you will say, oh, the mathematical function that would implement this has a richer signature because you don't just get an integer back, you might get a constant back, like the exception, right? And similarly, in Haskell, what we call pure can usually raise exceptions or diverge. So it will look more like this, right? Like an integer or an exception, and injected into that like divergence, right? The bottom element. And for programs like C or Java, you get these horrible signatures, and you can kind of see how much harder it is to reason about, right? Not just for humans, but also for a compiler. And many years ago, David Turner had a really nice paper about strong functional programming, where he argued we should really be most of the time in this total one, and not in the pure one. There was his main objection, whether it would be maybe exceptions or divergence. So he wanted like strong functional programming. And I think with Coca, you can see usually like 70% of your program is like in the total fragment. It's really satisfying, right? That's most I'm going to say about the Coca language, but there's lots of more stuff to explore. But I want to focus on this back-end part. Like, how do we get the functional programming dream of also getting performance? And I want to show a bit how this Perseus stuff works, because it's such an essential ingredient, not just to generate C, but also if you know that things are unique, you can often do in-place updates. So let's look at it. A beautiful sculpture of the real Perseus. It's amazing. I've seen it in real life. If you get the opportunity, please go. So here's maybe a little step back. People do reference counting themselves, right? In languages like C with like shared pointers, or Rust with like a drop trait, or a nim with a finally. And usually these are scope-based, right? The destructor runs at the end of the scope. And if you would take a program like this, where you create a huge list, and then you map over that list XS, and you get a new list YS, and you're going to print it, then in those languages, you usually do the drops at the end of the scope. So in the end, you drop XS and YS, and drop means decrement the reference count. If it becomes 0, then drop your children and free the actual cell, right? And I think in many languages it works like this, but it's too late because you do it scope-based. At the time of print, both of these lists are in memory. So you really, if it's a really big list, you're kind of doubling your memory because you could do much better. And this is what Perseus is doing. What it's doing instead, it doesn't drop at the end of the scope, but as soon as something is no longer live. So it passes kind of ownership of the access list, in this case, to the map. And while the map goes through it, it will deallocate decrement reference counts on every node, and then it will allocate the new list YS, and then that's passed to print, which will deallocate while it's printing. And now, at any point in time, you have kind of one list in memory, right? You halve the memory usage. And in practice, this is usually important, like this really occurs. It's also really hard to do it by hand, or to build it on top of destructors or scope-based things. And that's why Perseus is important. The compiler has to do it for you, right? It can easily keep track of this. Just hard for humans to do. So if you look at the map function, and we pass this ownership, what will Perseus do? It will say, well, when I match on access, it's kind of no longer used. So I'm gonna, it should be grayish here, but I messed up again. So Perseus will insert these instructions for you. So that's the automatic part, right? So instead of a garbage collector, it does this. And it will, you can see here, we create new references to X and XS. So you will increment the reference counts, you will top them, and then we'll drop XS. And if XS happen to be unique, this will be where you drop the children and free it. There's a beautiful analysis you can do to make this work. And then you can run it, and it's kind of behaves like a garbage collector, right? Except we do all the reference counting. And now you can kind of do nice peephole optimizations on these dop and drops. So I'm going to show you. There's actually a real cool property. It's garbage free. Like for any program, use the minimal memory necessary for that program. So at any point in time, there's no garbage in the heap, right? You free things as soon as they can be freed. It's actually really cool. So here, now we can do actually optimizations on this. So first I can do, I will always enter a if statement explicitly. So I will say, if the reference count is unique, then, and now I do both branches the same thing, right? But I'm going to optimize it, because I know in the bottom branch, well, if it's not unique, I know when I decrement the reference count, it will never be 0. So I can just decrement the reference count without doing anything more, so it's a little bit more efficient. And also, I know that if it's unique, if I'm going to drop access, I'm going to drop its children and then free it. So I can inline that too, because that will always happen, right? Because it's unique. And now you see, oh, there's a lot of drop x and a xx drop xx. So those fuse together. We can just get rid of them. And now it's just a free left there. And then we can do even a little bit better, because I'm going to see that later I need a con cell. So why would I free a con cell here and then like allocate it there, right? So instead of freeing, I'm going to return the address instead. So now I'm returning the address of the thing to be reused, right? And in the other branch, I'll return null, because there's nothing to reuse. So now we get a little addresses at runtime. And then I say, at the const node, I say, allocate there, right? If it's not null, just use that. And now it's in place. So when I'm mapping over a list, and the list that passed in is unique at runtime, it will reuse every console while it goes through it. And this is really nice. It's like easy to optimize in a way, right? And this allows a lot of the performance that Coca has by reusing existing cells. It turns out that you can make a beautiful calculus to do this. Read the papers. And you can kind of see it's like rather elegant, right? And this is like a type system. So you can consume like resources, and you have a linear environment. So the X must be in your environment, and you can like consume it. And sometimes if you want to just get rid of it, you have to explicitly drop it. So it's very reminiscent of linear type systems. And sometimes you can borrow resources if you promise to use them later. So you can skip all the reference counting. And I think it's a really nice like kind of type system that says if you adhere to this, it's sound, right? It's correct. Your reference counting is correct. But doesn't mean yet you're garbage free. You could kind of delay all the drops to the end of your program, and it would still be well typed. So then there's a syntax directed version that satisfies these rules, and that one has the garbage-free property, right? And there's actually different points in the design space too that you can really study well once you have like a nice formalization like this. So this is, I think, a very powerful part of this, and maybe understudied. So any PhDs, maybe take a look there. I think there's fruitful stuff to be done. I'm going to skip all the dark sides about cycles and atomics because I'm out of time, I think, otherwise. But ask me later. I want to talk a bit about what this system enables, right? So we call it functional but in place algorithms. And it's a bit like if we know as functional programmers, if you write something in a tail call position, like a recursive function, then we know, the compiler will compile it really efficiently with a while loop, right? And here's the same thing. Like we know that this reuse analysis that we just saw lets us write mutating algorithms in a purely functional way. Just like the map function is it under the hood now mutating in place, but it's still a purely functional description. And I want to show that actually with the initial example when I showed like the balancing tree. Well, let's try to write it in a tail recursive style, and to do that we need a zipper. So here we have a red and black colors, and then we have a tree with nodes of a certain color with left and right childs or leaves. And then the zipper is like the derivative of this tree. So we either came from the right when we go down the tree, and we have the rest of the zipper up there, or we came from the left and we have the rest of the zipper at the left part, or we're done, right? This is kind of the cursor down the tree. And here's like an example of that. Once I have a zipper and a tree down here, I can move up the zipper to produce a tree. So basically I say, well, if I came from the right, then make a new node with the tree on the right side. And otherwise, if I came from the left, make a new node with the tree on the left side. And here you can already see, like, here's this reuse is going to happen here, right? Because these nodes, I match on the node R, and I create a node, and they're the same size. So what we just saw with this Perseus stuff, if the zipper is unique, like not shared, then all the nodes will be reused, like in place. And we can kind of see the same with insertion. When we go down the tree, we maybe create, we came from the left, or we came from the right over here. And again, this node can be reused in place for the node L or the node R, right? And when we go balancing right up, same happens. Like we will match on 2 of these nodes, and each can be reused. So as long as it's unique at runtime, they will all be reused in place. And we get this really cool, I kind of try to illustrate it here. So if we go inserting, we start with a done zipper. And if we go one down, it'll the zipper becomes bigger. And it has a node L type because we went to the left. And then again, right, we have a node L type because we went to the right. And then when we move up, the pointer switch again. And you can kind of see this pointer like turning around, right? And this is really the pointer reversal tricks that people use in C land, but now we do it in a purely typed, beautiful, functional way. And so under the hood, it uses pointer reversal, and this is compiled, but we never see that, right, in the beautiful functional code. So here, I think I have the tree here, like in Coca. You can kind of see it's working here. And you see the move up with the zipper, and you see the balancing. And you see balancing is quite complicated, and insertion. And many years ago, I showed this this idea already to John Hughes here, one of my heroes of functional programming, sitting right there. And he said, Dan, this is no good, because you say, like, Perseus will make sure that all of this is in place, but I'm not sure, right? Maybe, like, this looks pretty complicated. I have to, like, eyeball it, that, like, node R matches node, and how do I know it's the same size, right? So here, for example. So here we now added, like, there's another type system you can run, which Coca does, and it can check if these functions are fully in place or not, right? So you can actually write here, for example, you can write here tail, to say, it's a tail recursive function. Well, it clearly is, like move up, move up. But you can say a little bit more. You don't say just it uses no stack space. You can say FIP here, fully in place. And it means if the arguments are unique, this will not allocate or deallocate or use any stack space. So it's a very strong statement, which gives you, so here, for example, with the balancing, right? Every time there's one node, there's like another node. So this clearly is FIP2. Let me see. Oh, well, maybe not. It's not FIP. Oh, it says it allocates at most 1, but was declared as allocating nothing, right? So I'm trying to cheat here. So when you look carefully, so you can't cheat on this type system. Sometimes it has to allocate a node, namely a newly inserted node. That makes a lot of sense because we're balancing up. So then FIP, you can say, well, I'm allowed to allocate one thing. So you can write a FIP1, right? So, but this is recursive. At total, right, it allocates 1, not like at each recursion. That would be defeating the purpose, right? And you can keep going. Like, I think this one is, FIP1, 2, insertion, yeah. An insert will be FIP1. Well, so you can go and, like, annotate more, right, to make sure, like, yes, it's actually getting the reuse. Which is really powerful, I think. Unlike, say, Rust, where you have all kinds of weird types, right? Like box or RC or ARC, or right? Here we express that it's fully in place with just a little keyword on your function, which I really like, right? It's very declarative. Also, if it's like untrue, like if I fake it, it'll still work. Like it still runs. It's a warning, right? It doesn't change the semantics of the program in any way. Another thing I like about this is, unlike, say, linear type systems, I don't want to create families of functions. So if I want to have one map function, that's like the obvious signature. I don't want, like, say in C++, I have to choose, will it be an in-place updating map or a copying map, right? I just want one. I don't want families of things. And it's the same with linear types. It's usually very hard to abstract over it, right? Here, by making it a runtime check, the uniqueness or the linearity, we don't get families of functions, right? You write the obvious insert with the obvious type signature, and that's it, right? I can also run it. Maybe you remember in the beginning I said this program, if I do it in C++, actually I can show you how that looks in C++. That's kind of nice too, because sometimes people say, oh, what's up with all this red, black stuff? It looks so complicated. Well, this is the LLVM implementation of red-black trees, and it's just way more, like it's really hard to say if it's right or not, right? Like I think even like reassigning nodes like halfway, so W here means something else, if the if statement was taken or not. Or, it's just wild, right? But it was very fast. It was 0.35 seconds. So let's see, I'll do a live demo. I'll compile my Coca program, which you know, has now beautiful transformations right there. So if you run it, optimized, it'll be 0.388. So it was 3.5 for the C++ version, 3.88 for the Coca version, but purely functional, right? Like, and it will copy on demand, and it's just amazing, honestly, like that we can get this. And to me, this is kind of, the glimpse of the dream, right? And now feel like, I think we can get there, right? Maybe not yet for all programs, but here is a non-trivial example, right? With a, beating a non-trivial implementation in C++. Let me see. Oh man, okay, I'm gonna hurry a bit more. I wanted to say that the FIP check, which is mostly by Anton Lorenz's work when he did an internship, is very beautiful too. It's like a subset of the Perseus calculus, which is very satisfying. And you can run it up front, and that does the checking if some things are fully in place or not. And it builds also on the reuse credits, which is inspired by Espinal, and Martin Hoffman did like a real nice calculus in the early 2000s about, they also tried to apply functional programming to like low-level memory management, and they had a similar kind of style, so that was very nice. I think, Gerard Huet had like a really nice paper about zippers many years ago, and he already kind of said like, oh man, this can be done in place. And well, now we have it, right? The FIP calculus makes this intuition really precise. So Coca does a lot more to get that great benchmark results. It does a lot of specialization and constant matching, and then in the end, it generates pretty good C code that translates to pretty tight assembly code. Don't have to go through it now, but you can kind of see there's a very small while loop there for folding over trees that gives us that performance, right? So in the end, we can really get there. One thing that you notice here is this free call here, me free, like a memalloc free. And that was really a problem in the beginning. The allocators were not fast enough for lots of small object allocations. I'm going to skip it because you already saw it was fast. And one side quest that started when I was working with this, with Leo Demura and Sebastian Ulrich and Ning Ning and others, was, man, we need maybe a better allocator. So we implemented this better allocator, and that became its own project called memalloc. And unfortunately, because, since C, so it's kind of embarrassment for true functional programming, but it became really popular. So I want Coca to be a giant success, but memalloc became a giant success. And it has many GitHub stars for a C project like this, and it's super concurrent and scalable and widely used by many people. It really started to become real when the Bing URP service took it as their allocator. It gave huge performance increases, and now it's in many places. I often don't know because people only tell me when there's something wrong. But it's a lot. Like this Rust package here. I don't know if I can click on it. Nah. Oh, well, there we go. Right. There are 51 million downloads, right? Like it's 100,000 a day or something. It's just a package, right, of memalloc around the Rust thing. So it's just big. And yeah, it's in C Python, right? In No-Gil. Sam Gross did this. He's the C, what is it? PyTorch creator, and many other places. Check out Houdini if you have time. So cool. Like Houdini does like special effects for movies, and memalloc was used when you saw maybe what's called Mickey 17, very fun movie. Memalloc is running right there, right, doing the animations. We often see that. So we had this big service at Bing, and there was a lot of variation in the overall system stability. But after memalloc, it's like ping. It's like really fun to see, right? Like how it helps with lots of stuff. Perforce is used for game studios a lot, for big binary assets instead of Git. Incredible performance benefits, right? Just crazy against many very serious allocators, like JMalloc is from Meta, and these other allocators are maybe also very well known. And then, it does really well, right? So that's great to see. And just 3 days ago, Ryu Ueyama, he made the mold parallel linker. It's very popular nowadays. It's very well designed. Actually, a great paper to read, how you parallelize like a linker. And he wrote that just using memalloc made it like, I'm not sure how to read this, 30% faster? Something. It made it faster, and it worked out really well, right? Another thing he noticed is that they made a really fast bump pointer allocator where they would never free, but it's slower than memalloc, right? I'll show you later why. Because you would think, if I just bump point allocate and never free, I'm going to be faster than the best allocator, right? But it's often not the case, right? And I'll show you too. So I wanted to show you a bit of memalloc because it's so successful, but also maybe from a functional perspective, right? I think when we make this, we're functional programmers, so we really think about clear data structures. There's no static global variables, right? Everything's contained in a sub-process structure. I don't look up the thread local state in some register. No, I pass it as a parameter, right? Everything's like very functionally designed, I would say, right? And there's this old quote by Fred Brooks in the mythical Man Month. It's from the 70s. I'll translate it to modern speak. So, show me your code and conceal your types, and I shall be mystified. But show me your type declarations, and I won't usually need your code. It'll be obvious, right? And I think this is how I designed the memalloc structures too. And this really helped with other people like Sam Gross for C Python, because he could look at these structures and be like, okay, I can see how it works. I can visit all the blocks for the cycle collector in Python, for example, right? So trying to find simplicity. It's fast. I think a cool thing is that if you look, so the red is memalloc, and the rest is other allocators, and these are really torturous benchmarks. And you can see that many allocators, on some particular kinds of benchmarks, they suddenly do really bad. Well, most of the time they do fine, right? And it switches too. And memalloc is pretty good at avoiding bad cases. So it doesn't go off the charts, literally. That sometimes happens with others. So that's a nice thing too. And I think part of that is just keep it simple and well structured. Then you'll notice, right, if this can happen or not, if you do any linear operations or not. Since there's not much time left, I only have 11 minutes, I'll skip ahead a bit. So here's the main allocation routine. And I'm going to go through it. So first, we're going to look up the thread local heap. I usually call it a theep nowadays. But we use a little trick here. We make sure it's never null. So we always point to some valid heap, and it may be like an empty one. And we don't do null because now we don't have to do an extra test, right? And then we say, we're going to round the size to an index. We're going to round it to like a whole word. And then we say, we will look up a little page directly in the heap that corresponds to those objects of that size. And again, I make sure there's always a valid pointer. So again, there's no null check, right? If it's empty, I'll make sure the free list is empty, because then we get the block from the head of the free list, and now there's only kind of one branch that needs to be checked, right? So we avoided a bunch of branches by avoiding the nulls, right? And then you pop from the free list, and unfortunately we also need to count how many things are in use, because then at the free we know when a page is becoming available again. In this code, maybe another cool thing, right? Like keep things simple. It's always a free list and never a like bump pointer. Often when you have an initial one, you can say, oh, I can just bump it up instead of having a list. But now you have special cases again with if statements and stuff. We want to avoid it. So we make everything very regular with one slow path. That is the generic alloc, which is slower. And then you get like really nice assembly. And for runtime systems, you can really do even better than this. This is already very tight. But like I said, in Coca, we already pass a thread local state to every function, right? So we don't have to look it up anywhere else, like a thread local variable. We already have it, so we can skip those first 3 instructions. And then, well, because I'm compiling it, I know the size of things. So if I allocate a cons node, I already know it's not going to be bigger than 1024. So I can skip those 2 instructions too to check for large sizes. And then we round the size. Well, I don't have to do that either because it's statically compiled. I can like round it up front. So now you only have these 8 instructions down here for allocation, right, with 1 branch. And this is fast, right? This is starting to become competitive with like a bump pointer garbage collector or something. And with free, it's kind of the same thing. I don't have time. I underestimated how long it takes, so I'm going to skip through the free. But you can also do a very efficient thing. 8 minutes, eh? I'll say a little bit about this, because this is a very important part of memalloc. It's very scalable across threads. And I want to kind of show how, because this is maybe the main difficulty with writing a allocator, that one thread allocates something locally, doesn't need any locks, but then another thread is going to free it. Like usually there's like on services, there's like one thread that gets all the requests and allocates a ton, and there's another thread that kind of frees it all. So how do you deal with this? Because now you have 2 threads accessing the same thing, and usually allocators have nowadays, like the good ones, like JMalloc or TCMalloc, they have lots of fancy data structures to synchronize this stuff. Like, and they kind of send messages like what is free or something. And I wanted to do something simpler and smaller. And that's what we try to do. And the idea is like inspired by randomized algorithms. So again, like if you take perfectly balanced trees, you just saw it, a lot of work to balance them right? It's very complicated, but they're perfectly balanced. But you can also kind of take the easy way out, and you just take a random oracle and you just split the tree, randomly every once in a while, and now it looks like this. How beautiful is that, right? I think I shall never see a poem as lovely as a tree. And now it's just also balanced enough, right? And even maybe more beautiful. And this is what I try to do with memalloc too. So instead of having one free list, like in the entire heap, we have like one free list per page, per 64K. And actually more than one free list. We have like a local free list, and we also have a thread free list. So 3 lists per page. And then there's thousands of pages in the heap. So there's thousands of these little free lists. But now there's a little contention between them, right? There's all these little thread free lists. So if some thread allocates something, and then the other thread tries to free it, it can do like a single compare and swap on the thread free of that particular thread, right? One atomic compare and swap. And normally, well, usually by a random chance, because there's so many, it will be not contended. And an uncontended compare and swap is really fast on modern hardware. So I think on older hardware that didn't hold, but nowadays it's integrated with the cache protocol. So if it's uncontended, you're kind of good. And now I don't need any fancy data structures to synchronize. I just have this one compare and swap, and it'll do the right thing. And that, I think, is key to the scalability of memalloc that people see in practice, right? And the other thing you get is good cache locality. So if you have one big list, that often happens when you allocate new stuff, and it's like a big free list spread throughout all the memory, and you allocate like a new list, say, right, with P, well, then your elements may also start to become spread through memory over time. But if you keep like all these little lists, then if you allocate your new elements, they will be in the same page most of the time, right? So you keep things much more local together. And this is why with the mold linker, the bump pointer was slower, right? It has much less good cache behavior, while memalloc will be allocating and freeing all the time in mostly the same pages that are like hot in the cache. So good things. Since I am running out of time, I will skip through this, although it's very interesting. Maybe ask me later. There's a huge service at Microsoft, like 768 gigabyte machines. It's like 200,000 of those running. And with memalloc, it will always run out of memory. So we put a lot of effort into that tension between the scalability and using the least memory possible, and we got there. So again, we can like integrate it with a compare and swap, but I'll skip through it because no time. And then we got like great results, right? So we suddenly at 60% of those 768 gigabytes. So now you can like either have less machines or more tenants, right, on one machine, which is good news for me and Microsoft, I guess, right? Thanks to everyone in that team. There was a lot of work to get this done. I wanted to, in the last 3 minutes, I wanted to highlight, because this is kind of part of this whole, like can the dream work? I wanted to highlight something like very neat, called first-class constructor context. And I want to look one more time at the map function. So here we see the standard map function. It's not tail recursive and a linear stack, right? And then one thing you can do is use an accumulator, which we saw earlier with the trees. We had the zipper, and this is, what is the zipper for lists? Well, it is a list, right? So what people usually do, you accumulate into a list, and in the end you reverse it. This is kind of the move up of the zipper, except because it's a list, it's so easy. You can just use a list. But it's not great, right? We walk through it, and then in the end, we have to we make a new list, and then we have to reverse the whole list. And for example, in the OCaml containers library, they have this kind of code, because the reversing is so expensive. They're gonna like collect tuples of things, and then we like reverse faster, because now there's like 9 elements per original element, etc. So this is not the FP dream, because now we kind of let go of like the simple map function, and it became really complicated, right, for efficiency. So something that Coca nowadays has are first-class constructor contexts. So you can create a data structure with a hole in it, like here a list with a hole for the tail. It's a context of a list. Or here a tree with a hole somewhere down there. It's a context of a tree. And then you can fill in the hole with ++ dot. So I can fill in the hole here with like the singleton list 3, and then I get the list 1, 2, 3. Or I fill here the leaf node in that hole, and then I get a node with leaf. And you can already see that if I know that the thing is unique at runtime, which we know because we use Perseus, I can update a hole in place. I'll just maintain 2 pointers to the top and to the hole, and then I can just update in place. So this can be very efficient. And then you can compose context too, of course. So you write in the initial hole here, you write the second one, and you get a bigger context, right? One hole all the time, right? There's always a linear path to it. And this works perfect with Perseus, because we know when things are unique, and we can just update in place. But we also can give it a functional semantics by saying, it's just like function composition. But the implementation under the hood can do this in-place updating. And here's that, it's kind of like graphically shown, right? That what we actually do at runtime for these contexts is maintain 2 pointers called mean and meter tuples. And mean and meter already had a nice paper of this in Popple 98. And then we can update the whole in place, right? And we keep track of the top all the time. So in the end, when we fill in the final hole, we can immediately return the entire data structure that we've created over time. And normally, in mean and meters work, you made a linear type system and stuff to make sure it's safe. But we don't need it. We already have Perseus, and we don't need like a special type system for that. And we can do very smart things, which I go through now. And then we can write map like this, a top-down map. So we start out with the empty context, and then when we do the mapping, we go through it, and then every time we extend the context with like one more cons node with a new hole, and in the end, we fill in the hole with nil, and then you get immediately the entire list back. And here's kind of how that goes, right? So first access points to this big list, and then we go to one element. Now we create, we reuse the cons cell in place for the context. And then, we reuse again in place. And we reuse again in place. And then, we fill in the nil. And we're done. So you go, like a C programmer, you go linearly to it. No allocation, nothing. And you end up with a list, right? Without any reversing or anything. And this is how you can do top-down algorithms. And we also created with Anton a beautiful tail recursion modulo context approach that automatically translates like a map function like this, where the recursive call is tail recursive modulo the constructor to the one using these contexts. So now the dream is kind of true because I can write my nice map, but I get like a super efficient in-place updating one most of the time, right? If the input is unique. This is just great, and we did this in a lot of more difficult things than map for trees. So we have here move to root trees, top down and bottom up with zippers, splay trees, zip trees. There's a Tarjan's recent invention called zip trees, and red-black trees. And you see Coca here with the red bar again, and then what is this color? Olive is C, and you can see we're really, really good, right, compared to the best C implementations. And that's just, to me, that shows, like, for these class of programs, we came really close to the functional programming dream. I think there's still a lot to cover, especially for arrays and state and stuff. But I'm very hopeful. It's a fruitful area. So if you're, want to do research in this area, please say hi to me. Many interns helped me over the years. Super awesome. Thanks, everyone. Tim Whiting gives a talk later today. He did a lot of work on the implementation of Coca. All of these are former interns of mine, and now they're all like esteemed professors at esteemed institutes, I think, most of them. Yes, everyone. And Anton is just done with his PhD. He wrote a really beautiful thesis, which I encourage everyone to read. Thank you so much. Also, I should buy new clothes. But I'm becoming the Esmond Gold of functional programming.
So great talk, and also a bunch of awesome work. One piece in particular, memalloc, I would love to use, but can't at the moment because there are issues around transparent huge pages, which is like a really ugly corner of the world, but an important one. And I'm curious, like, if you guys have thought about and done more work on trying to make memalloc play better with transparent huge pages on Linux.
I did, Ron. Yes, well, wow, it's a very specific question, right? So in Linux...
Everybody else here asked about,
right.
all sorts of other stuff, but I care about transparent huge pages.
Yeah. So this is really tricky with Linux. So it tries to use big pages, 2 megabyte pages, instead of 4K pages when possible, transparently. But often you now need to make these big pages, like you have to make room for it in the physical space because they're like pinned to specific addresses, and that can take time at runtime. And especially where you later split them up again by trying to decommit parts of it. And right, in practice, it's really important. And memalloc, nowadays, the most recent versions, really make sure you never break up these transparent huge pages, because that can be an issue, right? So nowadays, memalloc tracks what pieces are big, and it will only commit or decommit the whole part if they're aligned at the right spots. So yeah, talk more to me later, right? So you're not the only one running into this, right? It also shows how hard it is to do this well in general for programs, because it often depends on workloads and particular things. And I think Linux also underestimated that by making it transparent, but it's not, right? Like in practice, you have to really make choices, right? Thanks, right. Ron. Let's talk more, right?
Hello. Lovely functional but in place logo. But also the one with the little cats.
Ah, yes. Well, that's Ning Ning's creativity.
But also I was wondering, so your context notion on a few slides back, why exactly, again, do you need this to be a first-class notion over the implementation of it just as a Lambda? Is there an optimization that, or is there some more information that this gives you that you can't just assume with a normal Lambda?
No, we could do it with a normal Lambda, and then it would just work. And it would also work for this example. Like here, I'm sharing a context. That would just work fine if it's a Lambda, right? But because we want to do this in-place updating, we need to be very careful, because if we would do it here, where the context is shared, you get a cycle in this particular case. So yes, you can always implement it with functions, and also when you do proofs, you pretend it's these functions and function composition, but under the hood, we want to implement it using in-place updates. But to do that, you have to be very careful and make copies at the right points in time. So it's really, that's what I meant with first class. We're kind of trying to hide that we're doing this efficient thing behind the curtain, right? But we want to, we want you to think about it in terms of these semantics as lambdas. So if ever, right, like Coco would do something different than these semantics would give you, that would be wrong, right? That would be a bug. Does that answer the question?
Not entirely, I guess. Does the context, do you take any information from there being like an explicit context, I guess, invocation there that you couldn't get if you wrote it as a Lambda?
Yes. Good, yes. Yeah, so that's, the question is more about why do I need like this special keyword for context instead of like, why don't I write actual Lambda like this? Well, that's because I skipped over that because I have no time, but thank you for bringing it up, right? We compile these guys in a very special way where we put little indices at runtime to keep track of the path through the data structure to the whole. So here you would go in the first field and then the third field to find the whole. And by doing that, we can make copies of exactly the linear path in the context at runtime when needed. And that's kind of shown here. So the bold path here is the context path that we've kind of compiled in and keep track of at runtime. And when needed, we can make copies of exactly that path. So we maintain maximal sharing, but we make copies when needed, right? If things are shared more than you expect. Now, of course, this hardly happens, because when people write things with context, they're usually linear. But, you know, we want nice semantics. So. Yeah, please, yeah, thanks.
Okay, thank you.
Hey, Dan, really nice talk.
Thank you.
you gave an example in memalloc where you said when you use it in Coca, you get a performance optimization where you can delete quite a few operations at the front of memalloc. And this seems really interesting more generally just as a question of interoperation between different components built separately. Now, I'm guessing maybe you hacked a version of memalloc to put into Coca that you just deleted those operations, right? But like, I'm curious about, like, more generally, how do we compose these different units and get these kinds of performance specializations? Any thoughts on?
Yeah, no, it's a great question. And I think I do not do this secretly, especially because people get easily mad because you're already from Microsoft, so you're suspect. So everything's, free and open. And I do try, though, to expose lower level APIs, especially for runtime systems. And it's not yet crystallized exactly what's the best and what's needed. But yeah, no, these lower level calls are used by others as well. I think like more VM is using this, and maybe others, right? I don't always know. And for example, what I showed is kind of easy, right? I expose like free, small, constant size, an inlineable thing, and it will do the right thing. And I know there's even more possible, but that's harder to expose nicely. And I would love to talk more about it offline, right? But yeah, I think there's real opportunity there for synchronizing like these lower level things with the runtime systems. Yeah.
Hi. So reference counting, I've ran into that in a non-functional setting where very easy example or small example where cycles get introduced as a small doubly linked list. But in a purely functional setting, I was having, maybe it's because it's early morning, but I was having trouble thinking of a small example where a cycle is, I can obviously see a cycle. So for a second, I was like, maybe Coca just doesn't have to worry about cycles and with reference counting, but then you had a slide that you skipped over.
Yeah, I have a slide somewhere. I tried to, I don't. Oh, there, was it there? I saw the Darth Vader.
Yes,
there he
yes,
is.
yes.
It's like, oh no, right? Technical difficulties. So in Perseus, you can, if you have a cycle, it will not be collected. It will not be wrong, but that cycle will not be collected. Now and this, I think, maybe it's a wider thing. You should design your language in a way that you make that not common. So if you look at, Swift is a nice language. No shade on Swift, but Swift uses reference counting. It actually does the wrong thing often with the scope-based. But then it also, often people create cycles there because you create event handlers in an object and you do this in-place update. Now that the event handler points to the object that points to the event handlers. So a lot of little cycles, right? But in Coca, almost all data types are inductive. We don't do references. So it's really hard to make a cycle in the first place, right? So the only way to do it is with mutable references, which you shouldn't use if you can, right? And if you do, you'll have a maybe type in there, and at some point you can set it to nothing and break it yourself. And we hope that that's good enough, right? But there's definitely language design like coming in contact now, right? So Perseus wouldn't work so well for a language like Swift because of the cycles, right? Now in Swift, I think they actually have the same issue, and the programmers say, oh, this is a weak reference for the event handler. So there's also other ways, I guess, but I hope to avoid that in Coca, right?
You said it's very hard, but you didn't say it's impossible. So I'm curious about what that looks like.
Thank
you.
Hi, great talk. My question maybe is slightly related to the first question, but I didn't hear it right, so I'm just going to repeat it. So in memalloc, with having multiple free lists, does it ever run into issues with like inter-bucket fragmentation, or does it do anything to mitigate it as such?
So with memalloc, to battle fragmentation, each memalloc page is like 64K, has only objects of one size in it. So each free list is only of one size, and that kind of battles like fragmentation, right? I can actually show it here. So each heap has like up to the first 1024 like size classes, it has like direct pointers to pages that only have objects of that size in it, right? And its free lists are only of that size. So there's no fragmentation in that sense. It's bad if you allocate lots of differently sized things, which doesn't happen a lot in practice. And then this is maybe the bad part about allocators, which I really don't like, is that there's no optimal algorithm. You have to make choices. So binning, great for fragmentation, not great if you have like lots of differently sized things. And there's always these trade-offs that you have to make, right?
Thank you.
Yep, thanks.
So you have this very nice design that avoids multiple families of functions by doing dynamic checks. But have you looked at, considered using more static information to avoid more of those dynamic checks by adding linearity or usage information statically?
I thought about it, and I think it would be a good thing to research, right? But here, for example, with the map, right, there's one family, and you see there's the dynamic check, right, the if it's unique thing. If I would know that access is unique, I can skip that part, right? I can like directly reuse the address. So I think there's definitely, it would improve performance more because they won't be there. And also the bad path, the slow path, is also not there. So your code becomes more dense and so lots of good things, right? So I think it would combine well with a linear type system. And also, once it's linear, if you use a linear type, you also really guaranteed it never allocates, right? Like FIP says it never allocates if your inputs are linear. And an extra type system can give you that guarantee. So it is difficult, though, I think, to create linear type systems that are like lightweight in practice enough. Actually, Oxcaml does really cool stuff recently with modal types, which I encourage everyone to look at, where they try to do that, right? To have a lighter weight way to specify these things. But it's difficult. Yeah.
All right, let's thank Dan one more time.
Thanks so much. Thank you. I have stickers too, if you want stickers later. Also, I think there will be an announcement for the lunch for. Okay. Okay.
Stickers, and also in University Tower on the second floor today is the URM lunch.
Welcome, everyone, to the session on program analysis. We've got 4 exciting talks for you, 2 experience reports, and 2 regular papers. So to start us off, we have Zoe. Take it away.
Hi, everyone. Thank you, Ben, for the introduction. Welcome to this session. I'm excited to be here. Today, I will talk about an experiment that I did last February, mostly out of curiosity. I gave Cloud Code a task to prove that a compiler transformation is correct. And what happened over the next 5 days is the experience report that I'm presenting today. So let me zoom out first to motivate the experiment. So LLMs now write much of the world's code, and it's produced in a rate faster that humans can audit it. And the code is shipped oftentimes without being fully read or fully understood by the developers. So correctness is more important than ever. So a lot of people have been asking this question. Can LLMs generate not just code, but a machine-checked proof that the code is correct? And the fact that the proof is machine-checked let us move the trust from the one who wrote the proof, the LLM, to the proof checker. So this is the case study to prove that the a-normal form transformation of the Certico compiler is correct in ROC. And these were the rules of the game. The LLM agent was Cloud Code using Cloud Opus 4.6, and it writes all of the statements and the proof code from scratch. I guide and review the process, and I write no proof code. The result was about 6,000 lines of proof developed over about 95 hours. Let me talk a little bit about the setting, the CertiRoc compiler. So CertiRoc compiles the language of the ROC proof assistant to C and WebAssembly through a pipeline of verified transformations. So it first extracts a non-typed representation lambda box using MetaRoc, and then there are 2 routes into a functional intermediate representation, namely continuation passing style and a normal form. All of the orange arrows in the picture are verified, but the gray arrows are were not yet verified. So today we'll talk about this thick gray arrow. So the CPS transformation was proved correct a few years ago, and it uses a novel proof technique that combines syntactic simulations and step index logical relations. And it was developed over 2 or 3 months of sustained expert work. So for the ANF transformation, the same technique applies in principle, but the technical details differ in many ways. And it was left as future work. And in fact, at some point, I tried to do this proof by hand, and I was working for a few months on it on the side, but I got stuck. So I moved on. So recently, I gave the LLM the CPS proof as template, and I asked it to adapt it to the ANF transformation. And now, let me talk a little bit about the actual proof so that you can judge what the LLM was asked to do. And it will be brief, I promise. So when we want to prove that the transformation is correct, what we want to be proving is that all the behaviors of the target program are correctly captured in the behaviors of the source program. And a standard tool to do that is to prove a forward simulation. But this standard forward simulation diagram breaks for CPS for well-understood reasons. In particular, CPS introduces administrative reductions that break the simulation diagram, and in addition, new phrase binder names requires us to reason about alpha renaming. So instead of stating the correctness with a standard simulation, we use a logical relation. And in particular, we say this. Suppose that E evaluates to V. Then the translation of V behaves like the continuation applied to the translation of the value V. And this behaves like is a logical relation. And it is reflexive, transitive, and closed under beta and alpha equivalence, which is exactly what dissolves both obstacles. Now, This statement uses big step semantics, so it does not transfer to non-terminating programs. In order to prove that non-termination is preserved, we have to do something different. We instrument the evaluation relation with fuel, and we prove that if the source runs out of fuel, then so does the target, spending at least as much fuel. And this gives us preservation of non-terminating behaviors, and that's a standard technique. All right, that was the proof. And now let's talk about the experience. So the agent, Cloud Code, had access to the whole CertiRock repository and the whole CPS proof. And there was no ANF proof, no statements, no proofs. And then the prompt was to, I said to the agent, OK, here is the CPS proof. Apply this technique to prove the ANF transformation correct. All code must compile, and no admits should be left. And roughly the proof structure for both transformation is this. First, we have to prove semantic preservation, which is the main simulation theorem that I just showed you. Then we have to prove a first name invariance result that says that ANF results from different name supplies are logically related. Then we have to prove a relational computational correspondence, showing that the monadic implementation of the transformation refines a relational spec of the transformation that we use to show the semantic preservation. And then we show top-level theorems for whole and separately compiled programs. The experiment took about 94 hours start to finish. And day by day, it looked like that. The first 3 days were dedicated to the semantic preservation proof, which is by far the hardest result. Then the next day, the LLM proved first name invariance, and lastly, the correspondence and the top-level theorem. And below each day, you can see how much time the agent was working and how much time I was engaged. These are approximated from the session log. So in total, the agent was working for 54 hours, and I was working for about 13. And it was often left to run unattended for hours, even overnight, and it completed whole cases and lemmas. So this is how the process looked like, roughly. I gave high-level guidance in natural language. Basically, I planned the process. I told the LLM what proof to tackle next. I gave few mathematical hints. I reviewed the statements. I caught errors and these kind of things. Then the LLM argued about the proof in natural language. Then it wrote the proof script. It tried to compile the proof script, and then it was fixing all of the errors until the proof script was clean, and then it went to the next case. And this feedback loop with the proof checker is doing more than just compiling. It ensures that the LLM agent stays on track, ensuring that nothing gets built on top of invalid claims. And the strategy that the LLM followed was very similar to what I would do. So first, it sketched all of the cases and the skeleton of the proof, leaving inner admits, and it wrote helper lemma statements. And then it went ahead to discharge all of the inner admits and the outer lemmas, and that worked very well. And here are some other things that worked pretty well. So the LLM was very successful at adapting the proof technique in a new setting with different technical details. So it grasped the high-level strategy. It understood the logical relation, how to compose, how to use it, and it applied these things at the ANF transformation. It also did something else that I found interesting. It reasoned before proving. It was thinking in natural language for its proof case, and only when it was sure that the proof was correct, it would write the proof script. And if the proof script had no admits left, then it was usually logically correct, and it only required syntactic fixes to go through. It was also pretty good at routine proof labor, like setting up induction, cases analysis, finding lemmas from the code base, and the code quality was good. But let's talk about the failures. So the first one is probably the most instructive moment of the experiment because the LLM silently weakened the theorem. So in particular, the technique for proving divergence preservation does not apply to ANF as is, because the ANF transformation can reduce the number of steps that a program takes. So the LLM dropped the fuel bound from the theorem. It did not flag this, and the whole development kept compiling. And I did not catch that. And then only when it tried to prove the top-level theorem, we realized that, OK, divergence preservation is not provable in this way. Something else that didn't go very well is that for the monadic correspondence proof, which is conceptually the simplest proof, it copied the whole CPS proof, and it tried to fix it to apply to ANF, error by error, recompiling every time, and that was very frustrating. And in this particular file, I fixed 2 tactics by hand at the end, and these were the only 2 manual proof edits. Something else is that when it got stuck, it would erase proofs, admit them, without immediately returning back on its own. And I would have to explicitly remind it not to admit things, not to make assumptions that are not unless it is sure they are provable. But it did not always follow this advice because it did make false assumptions, it carried on, and then it had to go back and fix them. So the moral is that careful human review of the statements and progress, and most of all the statements, is essential. And in the paper, I described some more failure modes. So what did I do during the proof? I wrote 103 prompts, and most of them was simply steering, picking up the next task, and like advising about good proof hygiene. Few prompts gave real mathematical guidance. Sometimes the LLM was genuinely stuck in its reasoning, and I had to give it the proof argument or tell it how to correctly generalize a statement. What's interesting is that once I gave it the right argument, the LLM was pretty quick to make it proof code that works. And some of the prompts were nudges and redirections. And sometimes, for instance, that's my favorite, the LLM erased the proof and happily declared that the proof compiles. And I had to tell it, well, that's not exactly how it works. So here is the whole development by numbers. Some of these numbers I have already mentioned. What I want to say out loud here is that the whole process took about 800 invocations of the ROC proof checker. And the cost so the whole experiment was done within the limits of a Cloud Max subscription that costs $200 a month, and it stayed within limits. And the same tokens at API rates would have been about $1,000. So what does this mean instead of this one particular proof? Well, it suggests a new working paradigm for verified compilers. The human expert designs the proof strategy and the inference structure just once. And then the LLM mechanizes many transformations using that. And the certiorari compiler is a natural fit for that because the same logical relation proof already verifies a whole family of lambda INF to lambda INF transformations. It's following a similar pattern. So maybe we are already close to a future where new verified optimizations can be added on demand. But there is an open question. What happens in settings where there is no closely related proof template or well-understood proof technique? This has to be evaluated separately. And then there is also one important caveat. We said that the trust moves from the one who wrote the proof to the proof checker, but proof checkers can have bugs. And these bugs can be accidentally or even adversarially exploited by LLMs who do the proofs. And this is not hypothetical, because LLMs have been used to surface proofs in both the ROC and the lean proof checkers. But there are things we can do to mitigate that. First, as always, we need to keep kernels small and auditable, and then invest in building independent proof checkers and ideally formally verify them. We can also use advanced models to audit the proof checkers for bugs. So the gist of the experiment is this. We gave a clear template and expert guidance to the LLM, and it mechanized a substantial transformation correctness proof, compressing months of human work into days. All of the proof transcripts and the analysis scripts are public and artifact evaluated. And if you're interested in hearing more on AI and verification, I will be giving a keynote on Saturday at PPDP. Thank you very much.
Can you talk a little bit about the style of proof script that the LLM writes? So obviously different people have very different styles of writing rock proofs, and did it just adapt the style that you had written before, or does it have its own style? My experience is that they like to write everything out in extremely laborious and verbose detail. But I'm curious what yours is.
So it followed the general pattern of the repository. I didn't see anything that was extremely laborious, but also I do not use heavy proof automation. So yeah, also it heavily use subroles, and it will add comments to different subroles. So a lot of comments in the code, maybe a little bit more than I would like to. But I did not notice something in proofs that is very different from what I would have done.
Really nice talk, thank you. One of the interesting challenges with this approach is that you knew the right proof strategy ahead of time. So
Yes.
you knew that you didn't want to do a forward simulation, you wanted to do a logical relation. And there's many other instances of this in compilers projects, for example, register allocation. Probably you want to do translation validation. And so you would have to know that ahead of time in order to teach the LLM to do the right thing. What are your thoughts on, navigating that challenge? Right now, maybe it accelerates, if you already are an expert in the area of certified compiler development, it can accelerate your work, but what are your thoughts?
I have not used it to mechanize an entirely new transformation with an entirely new proof technique, so I cannot speak for that. There are some efforts in doing verified compilers from scratch, but I haven't seen anything published and peer-reviewed, so I cannot speak for that. But I think it's a very interesting question to evaluate going forward.
Okay, let me interrupt for 1 second. We've got lots of questions. We're going to take just one more so we can get on with the next talk.
Okay.
So.
Following up on the previous question, when you provided the CPF proof, was that proof scripts or was that a human written description?
It was a fully human written proof in Rock. It was mechanized in Rock, and I wrote it manually.
Okay, do you think it would succeed if you had given it what a natural language
Yes,
proof would
yes.
work?
I had some experiments like that. For instance, I had some pen and paper meta theory for a language, and then I gave it to Claude or GPT, I don't remember, and then it mechanized it in about a weekend. So it was pretty good at adapting the manual handwritten proofs to a mechanized setting.
Okay, let's thank the speaker. Our next talk is remote, so Nick will be joining us from Seattle momentarily.
Hello, do you hear me in the room?
Yes, we hear you. Take it away.
All right. Well, first off, I have an echo. First off, very sorry to not be there in person. We had a last-minute visa situation with one of the authors who was planning to come, and so we had a last-minute change to remote presentation. Thank you to the organizers for accommodating that, and my apologies. So this talk is actually it's great to follow Zoe here. It's very much in the same theme, where it's an experience report on using agents to do proofs of programs. It's joint work with Lev Ioannidis, Gabriel Ebner, Tahina Ramanandro, and Mathai Philippos at Microsoft Research. But I also want to give a special shout out to Shira Shamsu, Akhil Tuluri, and K.C. Sivaramakrishnan from IIT Madras and FP Launchpad, who've helped us a lot with this work. So we wrote this. We wrote this paper in February around the ICFP deadline, when we were amazed by the new capabilities of agents that had turned out since around December. I feel there's kind of a step change in capability improvement around that time. And the point of this paper was really to alert the ICFP community that if you haven't tried coding agents if you haven't tried them this year, you should try again. And things actually work now. They're much better than the code completion agents that you may have tried before. There's been lots of reports of them being good at general coding, but they're also extremely good at doing proofs, as Zoe was describing. And this paper is specifically about getting them to do proofs of imperative programs in F-star and Pulse. F-star is a higher order dependently typed functional programming language, and Pulse is a embedded DSL in F-star for imperative programming in concurrent separation logic. And it's these agents are really good at programming in F-star and Pulse, but I think they're pretty much good at programming in all proof languages, and probably, you know, the kinds of languages that are being designed at ICFP, they tend to be able to pick these languages up pretty quickly. So the experience report is in three parts. We report on three different experiments. The first is using these agents to build verified data structures in Pulse. These are things like, you know, sequential and concurrent data structures, things like linked lists and hash tables with chained buckets and AVL trees and so on, sequential data structures, but also things like counting semaphores and reader-writer locks and so on. And all of this together is on the order of around 10,000 lines of code and proof in Pulse. And this worked really quite smoothly, especially as you can see with on this column. Some of the simpler ones were entirely autonomous, and things like the reader-writer lock required me to give it some fairly detailed expert guidance. In the case of the reader-writer lock, I had to write down a 30-line invariant in semi-formal notation myself. The second experiment was about a verified circular buffer. There's a piece of production C code in the implementation of the Quick protocol at Microsoft. It's implemented in C, and one of its core data structures is a resizable, out-of-order circular buffer that receives that sort of puts Quick can receive packets out of order, and this data structure reconstructs the order using sequence numbers. And this data structure, we gave it the C code. We asked it to rewrite it in Pulse with code and proof, and in about 1,200 lines of Pulse, it's able to do this proof with minimal steering from us. Though at the time we had to actually, you know, it took several iterations of work with the agents, with critiquing the specs and so on, to get it to go through. The third experience was we wanted to see, you know, how these models would do at a large proof maintenance task. So we gave it a mark and sweep garbage collector for OCaml that Shira, Casey, and others had built and presented at. There's a paper at JR last year about it. I think it was presented at last year's OCaml workshop. It's about 50,000 lines of code and proof in F-star using low star, an older deprecated dialect of imperative programming in F-star. And we wanted to upgrade and port it to Pulse. This would have traditionally been a lot of work for a human expert. But with some oversight from mainly from Lef, we had agents ported in about 2 weeks. So there are some lessons learned from this, and these lessons, I think, are in the paper are lessons from February, and things move so fast. So I'm calling these lessons from, circa Opus 4.5, and there are three main categories of lessons that we report in the paper. The first is there's a kind of a syndrome of, the agent claims to have proven something, but is actually vacuous. The agent cheats and adds admits or has trivial specifications or writes the proofs in a way that they're actually disconnected from the code. And you have to be quite careful about making sure that you catch all these cheating modes. We also found then that we needed sort of detailed human steering. It wasn't realistic then to have an agent run all night and check the result in the morning. A human needed to sort of steer and catch mistakes early on, and that was quite fairly automatic, but still also quite interactive process. And then in the paper, we talk about what we see as the sort of new role of the proof engineer. And a lot of it, I think, is like figuring out how to decompose a task into phases, sometimes supply high-level proof ideas, and then, most importantly, to audit the specifications that turn out at the end, to make sure that what was proven was what was intended. These days, we continue to work in this direction, and these days with Opus 5 and GPT 5.6, some of these lessons are actually quite different. So on the vacuous verification side, I think this is mostly solved. I don't see blatant cheating anymore. You can say don't use admits, and it just doesn't use admits. And one still has to be careful to make sure that the statement of the top-level theorem actually relates to the artifact that is proven. But this too is mostly, I would say, solved. Detailed human steering, I don't think this is no longer. It doesn't seem to be necessary anymore in the kinds of experiments that we are doing. Agents run for hours and days and come back with a verified candidate, and we don't anymore do step-by-step steering. But what's more important than ever, I think, is for a proof engineer to work with typically a domain expert of the thing that you're trying to prove, to figure out how to decompose the task into phases, maybe supply high-level proof goals to explain what you want to prove, and spend a lot of time auditing what was proven, audit the specifications, and critique the specifications, and then launch fixes. And this whole process can take days or weeks to complete, but long-running agent tasks. So just for the rest of this talk, I kind of wanted to give a taste of what our more recent experience is. And there's two questions that we've been trying to ask. The first is, can agents maintain proofs? And the second is, how do agents fare when specifications become really complex? And for this, what we've been doing is, with help from the folks at FP Launchpad, we've been trying to evolve a mark and sweep collector into a generational GC for OCaml. So following discussions with Casey and Shira, we figured out a staging of the development to evolve the mark and sweep GC into a generational GC. And this staging involved 5 stages. The first was to build a verified allocator that's kind of a first fit free list composed with the mark and sweep phase. Then the next phase was to enhance the sweep so that it coalesces adjacent free blocks to reduce fragmentation in the heap. We then needed to relax a restriction in the original mark and sweep GC that Shira and others did, which required a mark stack that was at least as big as half the size of the heap, which was not realistic. So the phase 3 was to allow the mark stack to be bounded and for it to be a parameter. And then once we had that, the next phase was to add a minor heap and then do a Cheney style garbage collection, promoting objects from the minor to the major heap, and then finally to do the OCaml interop integrated inside the bytecode runtime, and then do benchmarking and optimization. It's interesting that stages 2 and 3 here actually ran in parallel, and then we had agents merge the two developments, and all of this actually worked out really smoothly. At the end, we end up with about 2,000 line garbage collector, generational collector, linked with the OCaml for bytecode runtime. The proofs are very large. They're about 80,000 lines of F-star and pulse proof. That's about twice the size of Shira's development on the mark and sweep collector. This is like a 40x proof overhead. A lot of it is infrastructure, like defining notions of graphs and so on that could be shared. But still, this kind of proof overhead is much larger than what we've seen before when doing SMT-backed proofs of other kinds of algorithms. I think this is a symptom of what some of the other questions in the first talk were talking about. The proofs tend to be agentic proofs are very detailed and verbose. At the end of the day, though, we don't audit the proofs, we audit the top-level specifications, and that's in the order of a few hundred lines of code. None of this code or any proof hints were written by hand. All input was natural language, but with a lot of specification critique. It's open source, and you can browse the code and proof at the link there. The main bit of guidance that I provided was to describe the property that I wanted to prove about this collector, which was to say that the reachable subgraph before the collection is isomorphic to the reachable subgraph after, and that all the non-pointer fields are changed. This is pretty much what I said in natural language. I suggested this criterion, and then the agent formalized it, and I had to review the formalization. I just want to give a flavor of what it looks like to audit a top-level spec at the end of the day. Doing this, it requires, I think, a fair amount of domain expertise to understand how OCaml actually represents various internal data structures, and spec expertise to read the proof, to read the spec and definitions, and it's easy to miss things. So this spec is the top-level spec of our generational collector. It's the spec of a total function in Pulse that has several arguments and a precondition, a result type, and a postcondition. And the main parts of the precondition are things like it requires the input heap to satisfy a heap shape invariant. It has preconditions on the size of the input gray stack. It has constraints on the way OCaml models the remembered set, which include major to minor pointers, and various conditions on the root set itself. And the postcondition contains the main isomorphism postcondition, which I had to review in detail as well. So it's not easy to review this. In fact, earlier this week, Akhil Tuluri and Shira Shamsu were reviewing this code and integrating it, trying to integrate it with the OCaml native code backend. And Akhil wrote to me on Zulip saying, I'll just read it out. A well-formed heap requires every pointer field to target an object in the object set. Infix objects are never in that set, so no field can point to an infix object. I've come across the infix issue when I was trying to integrate native code support for the Pulse verified GC. The well-formed heap conditions seem to be not exactly representative of what OCaml's well-formed heap is. So based on Akhil's feedback, and with 2 further days of agentic runs this week, and 45 commits later, we have about 15,000 lines of new proof, and Opus 5 has added support for infix pointers in this GC, or fixed support for infix pointers in this GC, and Akhil and Shira are now confirming that the fix is correct with their experiments. So just some takeaways at the end. Like, as we try to integrate this with OCaml, I'm pretty sure more bugs will be found, but every bug will be a specification bug. So the next one that we're looking at is, it turns out the way in which we model no scan tags in this GC is inaccurate, and we're trying to fix it. But in each of these cases, the mode of interaction seems to be, we describe what we think the spec bug is, and the agent patches the spec, code, and proof. In order to scale this to OCaml for real, we'll need to also add a few more features. The main ones on my mind are first to support heap expansion, and then to support incremental collection. And this will, I think, bring us close to parity with OCaml 4. But then there's lots more to do if we were to actually target a concurrent GC for OCaml 5. That's a whole other level of complexity. So finally, just some parting thoughts. Agents can develop and maintain large proof developments. The proofs are much messier than an expert human would write, but the main work that remains is for us to be able to read, understand, and audit specifications. We need tools to be able to do spec audit at scale. And I think there are two aspects to this. One is I think we should be thinking about better specification languages or better spec abstractions that promote terse, reusable specs that make review tractable. And I think spec testing is also an interesting angle to pursue. We've been looking at a technique that we call spots, or small proof-oriented tests, where we have the agent exercise the specs on small instances of the code. So for instance, a spot for this GC is proving that a small, say, 3-element heap, 3-object heap with infix pointers and so on actually satisfies the heap shape invariant and can be used to actually validate the precondition of the generational GC, call the generational GC, and prove that the result is what one expects. So these kinds of spec audit techniques, I think, are important, and it'll be interesting to see what the community comes up with in this space. The next frontier, I feel, is to figure out if production-grade verified software can be built in this way. I think we're at a point where we can kind of do research-grade verified software, but as we see with integration into OCaml, there's the means by which agents and domain experts and proof experts all interact. I think this is there's a lot to figure out here. So it's a fast-moving, exciting space with lots of problems which I haven't mentioned here as well, including things like access to tokens and environmental impacts and trust in the verifiers, which Zoe described. I think it's an interesting area for us to engage in, and there's a blog where I write about these things at the Rise MSR blog. So I'll stop there, and hope we have some time for questions.
Unfortunately, we are out of time for questions. Could the next speaker come up? Let's get you set up. Nick, I want to thank you for joining us at the last minute. This was a great talk. Okay, take it away.
Hello, I am Takahiro Sanada from Fukui Prefecture University. Today I will present our work programming backpropagation with reverse handlers for arrows. The central question of this talk is: can backpropagation for neural networks be programmed with effect handlers? Python-based frameworks are the de facto standard for neural network programming. They are extremely successful, but Python does not provide static type safety by default. And it was not designed specifically as a language for neural networks. We can instead use statically typed languages such as Haskell, OCaml, and Rust. There are also neural network libraries for these languages. However, our question is not simply which host language or library to use. We ask whether there is a mathematical foundation from which we can design a language for neural networks. One that separates an abstract network architecture from its concrete inference and training behavior. Our answer for the question is a common categorical account of neural networks and their programming language. The programming language is an arrow calculus with algebraic operations and handlers. A neural network layer is represented by an algebraic operation, and a handler assigns concrete behavior to that operations. Categorically, the key ingredients are algebras for strong promonads and homomorphisms between these algebras on a Cartesian reverse differential category. Before discussing these semantics, let me begin with a basic idea of effect handlers. An effect handler separates an abstract operation from its implementation behavior. Here is a small example with two operations, get and print. The computation first gets an integer by operation get, and then print its string representation. The handler says that get should return the number 2026. It also modifies print operation by adding the prefix ICFP. Finally, the return clause prints an exclamation mark. When the operation get is encountered, the variable k denotes the rest of the handled computation continuation. Its input is an integer. The handler resumes this continuation with the integer 2026. The print computation now proceeds to print with the string 2026. The print clause of the handler receives that string as S. It first print ICFP followed by S, and then resumes the continuation. The complete output is therefore ICFP 2026 and for exclamation mark. This example gives us the observation behind the paper. Sorry. With effect handlers, we combine abstract algebraic operations with behavior specified by handler clauses. Neural network programming has a similar shape. We combine an abstract collection of layers with their forward and backward behavior. This suggests the following question. Can we implement backpropagation with handlers? Our answer is yes. But we need a new kind of handler, which we call a reverse handler. First, we describe a neural network architecture symbolically. This example has two fully connected layers. The program invokes FC, fully connected layer, at location L0, binds its output to X1, and then invokes next fully connected layer at location L1. At this point, FC is only an operation symbol with an input and output type. The program determines the connectivity of the neural network and the location of its weight matrices. It does not yet determine how a layer performs inference or how its parameters are trained. We can assign inference behavior with an ordinary handler. When an FC operation is encountered, the handler retrieves the weight matrices from location L, multiplies it by the input, and applies activation function, and passes the result to the continuation. However, we cannot implement backpropagation with ordinary handlers. The problem is that an ordinary handler cannot express the required backward flow when the input and output types layer differ. Suppose suppose an operation has input type A and output type B. In ordinary arrow handler, the continuation takes B data of type B and eventually produces a fixed result type D. And the whole operation clause must produce the same type D. Backpropagation has a different type pattern. Backpropagation consists of two passes, forward and backward passes. We want to write the following clause QFC. This is forward pass, and this is the below is backward pass. And backpropagation would require this type judgment. This is different from the typing judgment of ordinary handler. This is exactly the mismatch that reverse handler resolves. A reverse handler splits each operation clause into two programs, QF and QB. The forward program takes an input of type A. It returns both output of type B and auxiliary data of a programmer chosen type D op. The B value is sent through the rest of the network continuation, while the auxiliary data is saved. After the rest of the network produced is a cotangent of type B, the backward program receives this cotangent together with the saved data. It then returns a cotangent of type A. This is a formal typing rule for reverse handler. And when we use the reverse handler, we use this typing rule. This split also makes the continuation linear in the operational sense. It is used exactly once, as in ordinary backpropagation. Now let us implement the two clauses for one fully connected layer. The forward clauses retrieves weight matrices from location L, and it returns W times X, and auxiliary data is W and X. The backward clause retrieves the output cotangent Y and retrieves W and X from the saved data Z. It updates the weight to weight W to W minus Y X transpose, and returns the gradient to the previous layer. To implement backpropagation for multi-layer perceptron, we use this handler, the reverse handler, like this. The local clauses compose into the usual global backpropagation algorithm. In the upper blue path, X0 is propagated through the forward clause for L0 and then through the clause for L1. The return clause computes the loss cotangent at the output. In the lower red path, that cotangent travels in the reverse order. First through the backward clause for L1, and then through the backward clause for L0. Why do we formulate this language using arrows rather than monads? To backpropagate gradient, we have to know types of both input and output of effect computations. Arrows are model of effect computation with input and output. For the denotational semantics of arrow is a strong promonad, a functor of this type, and arrow is denoted by the elements in AXY, and computations are sequences, not trees. Reverse handlers are interpreted by using a special algebra. To interpret reverse handler, we introduce a special algebra called a reverse algebra. Our language is interpreted using Cartesian reverse differential category, which is a category with reverse derivatives of morphisms. For a strong promonad on a CRDCX, we define this presheaf, this map. And we can show that this bracket A is a presheaf using reverse derivative structures of X. Moreover, if a sigma is a promonad generated by signature of operations, and we have elements of this type, then there is an A sigma algebra of this type, this on bracket A. By the universality of free algebras, there is a homomorphism induced by the freeness. And we can interpret reverse algebras by using this homomorphisms from the free algebra to reverse algebras. We proved the soundness and adequacy of denotational semantics with respect to operational semantics. There are many examples can be written in our language, MLP, residual networks, autoencoder, and so on, convolutional network, and so on. Reverse handlers separate abstract design from detailed behavior for back propagation. Conclusion, neural network layers can be programmed as algebraic operations for arrows. And the reverse handler gives each layer a forward and backward clause. We can separate abstract design of neural networks from its behavior. And the reverse handlers are interpreted by homomorphisms from the free algebra to reverse algebra on bracket A. Thank you.
Okay, we've got time for one quick question. Would the next speaker come up?
Hi. So you can give semantics to these reverse handlers in one of these CRDCs, right? Okay.
Yes.
So could you give some examples of CRDCs, like the ones that you use, and maybe some other ones that we could use them for?
One typical example is smooth. Objects are Rn, n-dimensional vector, and the morphisms is smooth map, and derivatives is ordinary differentiation.
Okay, thank you.
Thank you very much.
And let's thank the speaker again.
Thank you.
Okay, and now for the final talk of the session, Oscar will tell us about recursion in graded modal type theory.
Thanks. So this is joint work with Andreas Abel and Nils Anders Danielsson, and it's about some work that we've done within a formalization project on graded type theory that we've been working on for a few years now, together with some other contributors. And this formalization is essentially a fairly standard dependent type theory, Martin-Löf type theory, which has been extended with grades. And we use these grades to encode certain additional information. For instance, you can use this to encode security information for an information flow control application, or quantitative applications, like how many times does this function use its arguments when it's evaluated. And these quantitative applications have been sort of the main focus that we've had in the formalization project. But for this paper, what we were trying to look at is how we could handle recursion and incorporate recursion into this graded type theory, because it turns out that adding recursive functions, you have to deal with some issues that you don't run into for non-recursive functions. So essentially what we wanted to do was take some kind of recursive function over natural numbers, like for instance one of these, and try to figure out how many times these functions use their arguments. So taking like any individual of these functions is perhaps not too difficult to figure this out, but the point is that we want something that can be applied generally to any of these, no matter how weird recursive stuff we do, or even if we have no recursion at all. And we also wanted to do this in a way that avoids having to do over approximations as much as possible. So we could always say that any of these arguments are used somewhere between 0 and an infinite number of times. This wouldn't be too insightful, so we want to avoid this whenever we can. And the way we approach this is to, instead of sort of have some, well, add general functions with arbitrary recursion to the language, we're only going to add this recursive function, natric, which is of the standard eliminator that you get when you define the natural numbers as an inductive type. It's essentially like a fold for lists. So this only gives us a limited form of recursion, but it's sufficiently powerful to do all the things on the previous slide and a lot of other stuff as well. So I'll get back to more about this function and how we deal with it, but I'll start from the beginning by talking about the grades more generally. So what are grades? At least for our purposes, grades are elements of some partially ordered centering. And we use these grades to represent some number of uses of, for instance, a function argument. Exactly how this is done depends on what grades you choose to include in your SEMring and how you define the operators, which I won't get into. It's not terribly important for this talk. It's in the paper if you're interested. But we use these grades to annotate certain parts of the syntax with information about how many times things are used. So for instance, whenever we define a function, we need to put some grade annotations on the lambdas, telling us, in this case, that the first argument of the constant function will be used 1 time and the second argument will be used 0 times. And whenever we want to use this function, we similarly annotate the applications with corresponding grades. Of course, if we put these grades in the opposite order, that would be wrong. So we need some way of making sure that we don't do this, some kind of type system. And we do this with a separate typing judgment from the usual typing, which we denote with this black triangle. So gamma here is a context which assigns grades to each free variable instead of usual type. And this grade represents how many times this free variable would be used when the program T is evaluated. Essentially, we can think of this as counting the uses in T. So for instance, if we have an application like this, we would first count the uses in the function T, store those in the context gamma, count the uses in the function argument U, store those in delta. Then, because we have this grade P telling us that the function is going to use this argument P times, we scale the uses of that appear in the function argument by P, using the multiplication of the SEMring. And then we add the uses from the function with the plus operator of the SEMring. Another example is this if-then-else function, which is, or the eliminator for the Booleans. This has some similarities to the one for natural numbers, which we'll eventually get to. It doesn't have recursion, but it has the problem of having branching computation. We're going to either evaluate the true branch or the false branch. We don't know which one in advance, and things might be used a different number of times in the 2 branches. And the way we handle this is that we require these SEMrings of grades to also have an operator called meet, which gives us the greatest lower bound of the 2 arguments. And this meet operator represents some kind of approximation. If something is used, for instance, 1 time in the true branch and 0 times in the false branch, then the meet of 1 and 0 would represent something that's being used either 0 times or 1 time. And then we also have, in this case, the Boolean that we match on. We count those uses separately and add those to the approximated uses from the branches. Okay, so now we have essentially the pieces we need to look at recursion. This plus function is not the thing we actually want to use. It's not the netrec function, but we'll start with something a bit simpler. And just like the if-then-else function, there are 2 branches here. So surely we can just look at these branches individually, count the uses, and then take the meet. And if we try to do this, well, in the 0 branch, the second argument, n, is going to be used 1 time, clearly from the right-hand side. But in the successor case, n is being used as an argument to plus. So the number of times it's used would depend on how many times plus uses its arguments. But this is exactly the thing we're trying to figure out, so we don't get enough information just by looking at these 2 branches. But what we can do is to, instead of think of this function as a function with 2 different branches, think of it as having an infinite number of branches. The first argument could take any value between 0 and, well, any natural number. And if we were to unfold all of these possible options, it would be pretty clear to see that n is being used one time on the right-hand side in either case. At least if we consider the successor constructor to use this argument one time. And this is sort of this unfolding of all the infinitely many possible branches is the main idea that we're going to use when we add the snapdragon function. So like I said, this is essentially like a fold for lists. So we have some base case said that we apply in the 0 case, and some function s, which we use in the successor case, where we just apply the predecessor number and then apply the recursive call. But of course, in our syntax, we need these applications to be annotated with some grades telling us how many times they're used. So really, this snapdragon function also takes two grade arguments, p and r, with p for the predecessor and r for the recursive call. And so what we want to do is to figure out what the usage typing rule should look like for this. So as usual, we're going to just count the uses of the subterms, but we need to figure out what to put in place of the question mark. And to figure this out, we're using two tricks or ideas. The first is to take inspiration from what we do for if then else and other similar eliminators for simple types. And we're going to assume that we can count the uses of n, the number that we're matching on, separately from the uses of the branches. So what this means is that we assume that we can replace the question mark with something like this, where we take the uses of n, or in n, gamma, scale them by some grade x, which we have to figure out what it is, which represents how many times this number is used. And then we add some other context, chi, which should represent the uses in the branches. So chi should be independent of gamma. And the second trick is that in order to figure out what x and chi should be, we're going to do this sort of informal infinite unfolding of all the possible values for n. For each given value, and we can figure out what x and chi should be in that case, then combine all of those options with some kind of infinite meet over all of those options, or the greatest lower bound of all of them. So now all we have to do is figure out what these xi's and chi's are. And there's only a countably many infinite number of them, so it shouldn't be too hard. But really, we only need to look at a few cases. It turns out that we don't actually need to look at all of the unfolded versions of NATREC. We only need to look at the two basic ones. So starting with chi 0 will represent the uses in the branches when n is 0. And from how NATREC is defined, on the right-hand side, we only have said the base case. So the uses would just be given by delta z, the context for z. Then any other chi, so chi plus 1, would represent some successor case where we use the function s, which has uses delta s. We apply the predecessor number n, but we don't need to worry about that here because chi should be independent of the uses of the number. And we also apply the recursive call. But the recursive call, its uses would be given by the previous chi I. So in the end, we just get delta s from the use of s plus r times chi I for the r application of the recursive call. And we can do essentially just the same thing for x. In the 0 case, there's no explicit use of the number, but we do match on it, so we count that as a single use. And in the successor case, we have a p uses for the p application of the predecessor plus the recursive uses scaled by r. And this is the usage rule that we end up with. Of course, to actually use this, you need to figure out what these infinite meets or greatest lower bounds are. And to do that, you basically would need to instantiate this with some simmering. And from what we've tried in the paper, figuring out what these greatest lower bounds are for concrete sim rings is fairly straightforward. So there's one thing left that we need to do. We need to also show that the thing that we come up with is correct, that whatever number of uses it tells us is consistent with what actually happens when you run the program. And we do this by defining an abstract machine based on Zestoft's machine, where we add capability to track how many times variables are being used. So this machine is a call-by-name machine. There is essentially a call stack, but the important part is that there is a heap where the entries are associated with a grade. So we keep track of how many times these entries are allowed or supposed to be used. And then we show in the end that any well-typed program is going to have its variables and things like function arguments are going to be used as many times as specified. But the details of this are left for the paper. And so to sum up, the main thing that we do in the paper is to add or extend our graded type theory with a form of recursive functions over natural numbers. The main idea is to use a kind of infinite unfolding of an infinite number of branches. We show that this typing rule is correct. We also show in the paper that it is optimal in some sense, that we don't do unnecessary over-approximations. And perhaps most importantly, at least I think, is that all of this is formalized in Agda. There is a lot of code going into this, although admittedly not all of these 170,000 lines are relevant to the paper. It's a lot of things going on in this formalization now. But that was all. Thank you.
Okay, any questions? Come on up, let's take 1 or 2 minutes for questions.
Maybe one thing, do you think that one day this could become a built-in feature in Agda?
I think, I mean, there is an open issue on the GitHub about adding linear types. So this work is somewhat going in that direction of figuring out what you would need to do to add linear types. I don't know about adding like general graded types with arbitrary grade sim rings. That might be a bit too much, but I think linearity could happen at least.
Nice, thank you.
In the title of the talk, you have model. And do you have something to say about that?
No, not really. So modal is a bit of a leftover from when we started working on this. It's sort of been hanging around like this. When we started working on this, we only called this like modal type theory, which sort of got renamed to graded modal or just graded. It's a bit like the modal would maybe refer to having these modal operators, as was in the talk 2 days ago. We can define such a like modal operator with using sigma types. So they're somewhat around, but there's no real focus on them in the paper.
Okay, well, one thing that I was curious about is would it make sense to do the same kind of counting for code data?
That is also a question I would be interested in looking at, which we haven't done.
Okay. All right, let's thank the speaker. And this concludes the session. Lunch is next.
to the after lunch session. Oh, podium, yeah. Okay, good. We have Thiago, I believe, over
To the after
over
lunch
Zoom.
session.
Thiago, are you able to share your screen? We can.
Okay, good. We have Thiago, I believe, over to the after lunch session.
Good. So I'm happy to.
Can you see my slide?
Yeah, it looks great. So I'll go ahead and introduce you. So welcome everyone to the session on dependent types and proofs. So our first talk is by.
Can you see my slide? Yeah, it looks great. So I'll go ahead and introduce you. So welcome everyone to the session on dependent types and proofs. So our first talk is by. Can you see my slide? I'll go ahead and introduce you. So welcome everyone to the session on dependent types.
Yeah, I know. We're getting quite a bit of feedback, Thiago. So do you mind if you just mute for a moment? Yeah, I know. We're getting quite a bit of feedback, Thiago. So do you mind if you just mute for a moment? Yeah, I know. We're getting quite a bit of feedback, Thiago. So do you mind if you mute for a moment? Do we think that was the? Did that fix it, Alex? Yeah, I know. We're getting quite a bit of feedback. Okay, well, anyway, we'll keep going. So I introduced Thiago. So Thiago is going to talk about confluence techniques. Thiago, you can hopefully take it away, and hopefully we won't get any feedback. Well, we'll keep going. So I introduced Thiago.
So I'm still get some feedback here. Not sure if I'm the only one.
Hopefully take it away, and hopefully we won't get any feedback. I think they're working on it. We'll wait for the, see if we can, Alex, let me know when you're ready for me to.
So I cannot hear anything right now.
Okay, see if we can, okay, he's saying he can't hear anything right now. Alex, let me know when you're ready for me to.
So I cannot hear anything right now.
Okay, see if we can.
Can you hear me?
Okay, he's saying he can't hear anything right now. Alex, let me know when you're ready for me to.
So I cannot hear anything right now.
See if we can.
Can you hear me?
Okay, he's saying he can't hear anything. Alex, let me know when you're ready for me to.
So I cannot hear anything right now.
Say again, Alex?
Can you hear me?
Okay, he's saying. But we're getting the feedback still. My voice plays with feedback whenever I talk. Say again, Alex? Okay, should we try it? But we're getting the feedback still. All right, Thiago, why don't you go ahead and try? I'll pause you if we get technical issues on our side, but go ahead and take it away. Should we try it? But we're getting the feedback still. All right, Thiago, why don't you go ahead and try? I'll pause you if we get technical issues on our side, but go ahead and take it away. Should we try it? All right, Thiago.
Okay, so let me just hear if I'm getting feedback of myself.
Technical issues on our side.
Okay, so it seems to be fine, so I'll go with the talk now. Okay, so let me just hear if I'm getting feedback. Okay, so I'm actually getting feedback of myself, so okay, so it seems to be fine. So I don't know how to. Okay, maybe I'll just cut your audio and. Okay, so I won't be able to hear you, unfortunately. But okay, so it seems to be fine. So I don't know. I don't know any solution. Please tell me if you know of any other. Okay, so I won't be able to hear you, unfortunately. But okay, so it seems to be fine. So I don't know. I don't know any. Okay, so I'm gonna start. Can maybe you just put a message on the chat that you can hear me and everything is fine. There's no feedback on your side. So I don't stop, because then I'll move the slides and I won't be able to see any message. Put a message on the chat that you can hear me and everything is fine. There's no feedback on your side. So I don't stop, because then I'll move the slides and I won't be able to see any message. I'll go ahead then. A message on the chat that you can hear me and everything is fine. There's no feedback on your side. So I don't stop, because then I'll move the slides and I won't be able to see any message. I'll go ahead then. Okay, so thank you. So this is joint work with TU Winterwater, and before starting, let me say that all of the results that I'm going to talk about here have been formalized in ROC, and you can find a link to the formalization either on the article or on my website. So let me start by recalling what is dependent type theory. So it's the foundation of this very popular proof assistance that I guess you've heard of, Lean, ROC, and Agda. And really the defining feature of dependent type theory is that types can depend on terms. So for instance, we can consider the types of length indexed lists, which is called the type of vectors. And here we have a vector of length 3, and we see that 3, which is a term of type nat, also appears in the type. So we see this dependency in this example. Now, another very essential feature of type theory is conversion, which is an equational theory that dictates which terms are to be considered the same. So, for instance, we want to identify 3 with 1 plus 2 because they compute the same way. But now, because we have type dependency, then we should take this into account. So conversion impacts typing in the sense that if I have a vector of length 3, and well, 3 is convertible to 1 plus 2, so this is also a vector of length 1 plus 2. So this interaction, this interaction of conversion in typing is really one of the most intricate feature of dependent types, and in particular when we are doing any type checking, we also need to do some conversion checking in the process, which is something that does not have happen with non-dependent types. Now, historically, there's 2 ways in which we can define conversion, and differentiating between them is one of the points that we need to understand for the talk to make sense. So we have the approach of doing untyped conversion, in which we define conversion as an untyped equational theory between 2 untyped terms, like in the untyped lambda calculus. So we have an inference rule for untyped beta conversion, and then we add a bunch of rules saying, for instance, that conversion is symmetric, that lambda is a congruence with respect to conversion, etc. And this is the type of conversion that was used in the first dependent type systems, but is also used today in many projects like Dedukti and Metarock. Now, there are many benefits of untyped conversion, but one of them is that we can define conversion before defining typing. So there's no mutual dependency between the two, which simplifies some of the proofs. But the main point for this talk is that with untyped conversion, we have access to many confluence techniques that have been developed in untyped settings. So we have many papers by, for instance, by Takahashi, which is a very no paper, or confluence criteria that have been developed in high order rewriting. And by using this, we can show non-confusion properties that are very important. So they state, for instance, that pi is, to just recall the type of dependent functions, that pi is injective with respect to conversion. So if I have 2 pi's which are convertible, this is only possible if their domains and codomains are convertible. And these properties are quite important to establish the correctness of implementations of type theory. So this is the main application of confluence. Now, the second type of or flavor of conversion is typed conversion, in which we define it as a judgment mutually with the typing judgment. So here, for instance, when you look at beta conversion, we see that we actually have as premises that T and U have the expected types. And well, maybe this is controversial, but I have the impression, or at least, yeah, it seems to me that nowadays this is the standard way in which most people want to define conversion. There are many reasons for that, but I think that the main one is that we have a better connection with semantics with type conversion, because then we know how to show that the syntax can be assembled into initial models for usual notions of categorical semantics, like CWS and this kind of things, which are nowadays, I think, that the main notion of semantics that people consider. So there's a discussion in section 8 of the paper for more details about this and what's the problem with untyped conversion in this case. And this is also important for if you want to consider type theory as an internal language for instance, for set theory, or because to be able to justify this, we need to build a model of type theory into set theory, or if we're doing syntactic mathematics, then we need to build a model into the word that we're considering, if you're doing, for instance, syntactic compilability. So this is quite important to be able to justify these uses. But yeah, so unfortunately, the big problem with type conversion is that most of the literature on Confluence only targets the untyped case. So there are some exceptions, which are these 2 articles that I'm referring to here, but they target rather basic type theories. So this means that whenever we have to prove the injectivity property that I was talking about, we usually show them with complex logical relational arguments, which are normally heavier to prove than with confluence proofs, and also require a stronger meta theory, which in some cases is something that we would like to avoid. So this work is all about trying to have the best of both worlds, to keep type conversion, but try to develop confluence in this case. So what we do is that we show that confluence techniques can be scaled to reach type theories with type conversion. So beyond universes and pi types, which were the features that were considered in the two prior work that I just talked to you about, our confluence proofs handle many other things. So we have sigma types without eta, which is not very surprising, but then we also have Leaf types, this time with eta. So Leaf types basically take a type in a universe and then give you a type in the next universe, and then you have a constructor and a projection that allow you to simulate a weak form of cumulativity, as found in the AGDA standard library. Then we also consider, we handle definitional proof irrelevance, as can be found in Lean with prop or in Rock with sprop, which is basically a universe in which all types, for all types, all terms are convertible. And we also handle some inductive types, which is a bit less surprising. And to illustrate the extensibility of a proof, we also handle two flavors of proof irrelevant equality. So we also consider observational equality and Lean's equality eliminator, which has this strong nonlinear computation rule in which we compute the result as soon as we have an equality in which the 2 points of the equality are the same, regardless if the equality is REFO or not. So this is what they handle. So let me jump into talking a bit about how this is proved. So, like with most confluence proofs, we do this by introducing an orthogonal, sometimes called parallel reduction relation, except that here we have to have a typed judgment. So I won't give you the definition, but the main points that are interesting are the following. So first, the usual definition of orthogonal reduction and add the types, then we realize that we need to actually add some type annotations, because here, if I'm trying to invert the judgment that's in the conclusion, then there are many candidates for A and for B, and I don't know that all of them are convertible. So what we do, and this is also done in the prior work that I mentioned, is that we add all type annotations to the syntax, and then whenever we reduce, we need to make sure that the type annotations match. So this corresponds to the first two premises. Now it can seem a bit unsatisfying to add annotations, but actually having them in the syntax is good when interpreting the syntax into models. It helps with it, and it doesn't have any impact in implementation, because as I'm gonna talk about next, they can just be elaborated away. They do not show up in implementation, so this is not an issue. Then proof irrelevance actually can be handled in a kind of like trivial manner. So I didn't show on the other judgments, but we annotate the judgments with the level, the universe level of the type. So whenever we are reducing, whenever we're considering terms that have level omega, which correspond to prop, which is the irrelevant, proof irrelevant universe, then we can just reduce any term to any other term. So as you can see, this is not at all algorithmic, but the point of orthogonal reduction is not to be implemented, it's just to prove the confluence theorem, which will then give us all of the information that we'll need later to define the algorithm that will be implemented. Then we have lift, eta equality for lift. So this is just handled as an eta reduction rule. And the nonlinear rule for transp is treated as a conditional rule. So instead of having A both times on the left-hand side, which would pose some problems, we duplicate it, and then we ask that A and B are convertible. So the way that we define things because of the way we define things, we have orthogonal reduction included in conversion by construction. And then the main theorems is that, well, the main result is that whenever two terms are convertible, then they can be joined to a common reduct using orthogonal reduction, which follows from two lemmas. So first, the diamond property for orthogonal reduction. So this is the usual lemma that appears in this proof, but this time it's a bit harder because in the proof we need to keep track of these annotations and of their convertibility, as I was saying. And then we also need the inclusion of conversion into the reflexive symmetric transitive closure of orthogonal reduction, and this is actually a bit tricky in the types case. So this is also one of the main lemmas. And then, as a corollary, we derive all of the injectivity and non-confusion properties that we want, such as injectivity of pi and the fact that pi cannot be convertible to NAT. So once we have our confluence theorem, then the main application, like I was saying in the beginning, is to prove correctness of implementation, so of conversion and type checking algorithms. So for conversion checking, we consider a kind of reduce and compare algorithm for our theory, in which we use an algorithmic untyped full reduction judgment. So we just reduce the term until we reach a re-reducible form, and then we compare the two terms, as you can see. But of course, as I was saying, the core syntax is too verbose. We don't want to use that in implementations. So instead, this algorithm is defined over an erased syntax, and then we have an erasure function from the core syntax. So by proofs, I mean terms that have a type that is in SPROP, that is in the proof relevant universe, and we remove most annotations. So as you can see, if I have a P that has level omega, so this means that P is a proof, then I re-raise it to a dummy term box. And if I have an abstraction, I just erase all parameters. I just keep the body of the abstraction. And then the main result that we prove using confluence is that if I have two well-typed terms, and if the erasure, if when doing conversion checking with the erasure, I get a successful result, then the terms are indeed convertible. And we also have the converse provided normalization. So we cannot prove the converse without normalization because it actually would imply normalization. And this is not something that we can prove with confluence alone. And then we have also type checking. So we use this conversion checking algorithm to build a bidirectional type checking system for the system that I presented you, and that takes as input also user-friendly syntax in which we don't have to write all of these annotations. And once again, we prove soundness and partial correctness. I won't detail the precise statements for lack of time, but let me just insist on a point which I think is interesting, is that our completeness result is kind of like ecumenical in the sense that we handle both French and Swedish styles of completeness. So in the French or à la Roque style, we have, for instance, to add some annotations to some terms, or lambdas, they will be annotated with their domains. And on the Swedish style, whenever I want to write a regex, I need to put the type in the middle between the constructor and the eliminator. So we can handle both styles in a uniform way. So if you want to see more details about these, the conversion checking and type checking algorithms, I'll refer you to the sections 4 or 5 of our paper. Okay, so let me conclude. So we scaled confluence techniques to rich type theories with type conversion, and everything is formalized in ROC. We covered many interesting features, like proof relevance, eta for lift, the non-linear rule for trans, and I heard many times people saying that they didn't think that this could be handled with confluence. So this is one of the points of this work. And of course, the main application is to show correctness of conversion and type checking algorithms that operate on the usual non-annotated syntax that we use in proof assistance. So there are some limitations. We cannot handle eta for pi, sigma, or units. And this is detailed on section 7. This is actually quite interesting because eta for pi can actually be handled in the untyped case. So this is a difference that shows that not all techniques that work on the untyped case will also work in the typed one. So I think it also motivates why it's important to study confluence in the typed case. And yeah, so for me, the takeaway message is that the confluence is not at odds with type conversion, but rather with ITA. And then the question that remains, and I'm very interested in the answer, although I don't know how to answer it today, is that can we go beyond ITA for lift with these techniques? So yeah, I'll end with this, and thank you for your attention. And I'll unmute my mic. You. Said, can we go beyond ITA for lift with these techniques?
Okay, so we can do a quick question, if anybody has a question for Thiago. In that case, maybe I'll ask a question to Thiago. So question, you mentioned at the end that you can handle ADA in the untyped case, but not in the typed case. But it kind of seems like you maybe could attempt to port some of the ideas from the untyped case to the typed case. I was just curious, do you think there's any hope for solving it with that approach? What do you think? Kind of seems like you maybe could attempt to port some of the ideas from the untyped case to the typed case. I was just curious, do you think there's any hope for solving it?
So I'm sorry, I got a lot of feedback. I was unable to understand the question. I think there was a question, but I was unable to understand it.
Just the
Maybe
question.
if you write it, maybe I can try to answer.
Yeah, just about the future work and like how to extend the technique for ADA, and maybe you can say a little bit about what you'd like to do.
Maybe if you write it, maybe I can try to answer.
Yeah, just about the future work and like how to extend the technique for ADA, and maybe you can say a little bit about what you'd like to do.
Okay, so from what I got, the question is about the future work. So, okay, so I'll have to mute you to answer. Sorry. So from what I got, the question is about the limitations. So the problem with ITA for pi, sigma, and units. So I don't have any ideas how to handle it today, but let me just maybe comment on the problem of ITA for pi. So the thing is that ITA for pi on the untyped case, we can just treat it as a reduction, and the usual proof via the diamond property will go through. But the problem is that when we add types into the mix, then we realize that we actually need the straightening property in order to show the diamond property. However, the straightening property normally requires us to either, I mean, there's no easy syntactic proof of it that I know. It usually requires either normalization or confluence. So we end up in a kind of like loop, which is interesting because by going out, we can go outside of this loop with untyped conversion, because then we don't have types when doing the confluence proof. But yeah, so this shows that this trick only works indeed when we don't have any types, when you only consider untyped conversion. So I don't know how to do it today with type conversion, but I would be very interested to know it. So I'll meet you back. Only consider untyped conversion. So I don't know how to do it today with type conversion, but I would.
Good. Okay. Well, let's thank Thiago. Thank you, Thiago, for the talk. Discord is not even available. He's not. Yeah, excellent. Good. Hugo, are you able to hear us?
I can hear you.
Excellent. Okay. Well, in that case, I'd let Hugo take it away. This is an equational and graphical fixed point calculus. Go ahead, Hugo.
So good afternoon, everyone. If you can hear me, it means the AV team did a great job, so hats off to them. And I'm here to present our functional Perl, an equational and graphical fixed point calculus. And this is joint works with my colleagues at the Federal University of Rio de Janeiro, Hugo Nóbrega, João Paixão, and our undergraduate student, Gustavo. So what do I mean by equational in the title? Hopefully the functional programming community is already in the right vibe here. But when I say equational, I mean, say you want to prove that two sets are equal. One way to do that is to try to chain together a series of equivalences. Another is to work by mutual inclusion and try to say that one of set contains the other. Similarly, if you want to prove that two formulas are equivalent, the equational way would be to work with if and only if as much as you can, whereas the inequational way to do that would be to use implication. The downside of implication is that you can lose information as you go along. So if you can have the luxury of reasoning equationally, it's a positive thing. So in this paper, this is a case study about equational reasoning in the context of least fixed points. So I'm talking about looking for solutions to problems like f of x equals x. This is widely used to model all kinds of self-referential things, data types, data analysis, semantics. We had some talks of this idea over the previous talks in this conference. And the neat thing about what we did is that we used string diagram notation instead of the usual first-order logic notation. This, at first, it surprised me. I thought, oh, this is too esoteric and categorical to be practical. But I want to convince you that it's actually not as complicated as it seems, and it allows for cleaner and more discoverable proofs. So, as an example, I will use the rolling rule. The rolling rule is a theorem from the fixed point calculus, which was a collection of theorems from the mathematics of program construction group. And this theorem states that if you take the fixed point of f composes g, it's the same as f applied to the fixed point of g of f. You can kind of see this if you unroll the fixed point and peel off the outermost f. But the ironic thing is that if you want to prove this like a proper proof, this proof is not equational, despite this being an equational theorem with an equational statement designed for equational reasoning. So the culprit is that the specification of a least fixed point is not equational. So for here I'm saying the least fixed point of f is less than itself, and any other x that has the property is greater than the least element. Just a small technical parenthesis here. I'm talking about prefixed points where the comparison is a less than or equal instead of an equal. But as it turns out, this is complete. The least prefixed point is completely equivalent to the least fixed point, and it's more mathematically pleasant to work with. So we and others, we tend to use prefixed points from now on. But anyway, the big deal here is that unfortunately, this specification is not equational because not only is it split into two parts, so it invites a two-part proof, but also the second rule is an implication. And as I said previously, implications don't play nice with equational reasoning. So what can we do to address that? So we have a bag of tricks from the literature and the folklore. The first is this idea of indirect equality. Say if I want to prove that x is equal to y. One way to do that is to work by mutual inclusion. You prove that x is less than y and y is less than x. Another way is that if you have that x and y compare the same way against everyone else, then that means they must be equal. This invites another way to prove that x is equal to y. If you can take x less than z and rewrite it into y less than z, that means x must be equal to y. Moving on, this indirection trick also allows us to change the specification of a monotonic function into something that can be used as a rewrite step in an equational proof. So consider the original definition of monotonicity. A monotonic function is one that if you take x less than y and apply f to both sides, the order is preserved. But we don't like this because it's an implication, and implications don't play nice with equational reasoning. The formula on the bottom of the screen here, in the paper, we have a short proof that this is another way, equivalent way to specify what a monotonic function is. It's a bit of a mouthful to read out loud, but the important things to pay attention to is that we have introduced this indirection variable z here. So it's a similar trick to before. And the overall formula is an if and only if. So it can be used as a rewrite step in an equational proof. Continuing with this style of trick, we can specify least fixed points equationally. So we say that the least fixed point mu of f is less than y if and only if there exists another prefixed point x that is less than y. Again, the details of this proof are a nice exercise. You can find the answer in the paper. But for now, the important bit is that this new specification is a single rule, it's an if and only if, and it can be used as a rewrite step in the proof. So what's the good news? If we combine all those ideas together, we can get an equational proof of the rolling rule. See, every single step in this proof is an if and only if. And on the ends, you have something that fits the indirect equality principle. So we are proving that the least fixed point of f of g is equal to f applied to the least fixed point of g of f. Unfortunately, the intermediate steps are awful to look at. They are very complicated. There are way too many variables, and there's a lot of steps that are just fiddling and pushing the inequalities one way or the other. This is not a very nice proof, unfortunately. So can we do better than that? Well, yes. And the important thing is that you have to use the better abstractions. So the abstraction that I want to talk about here is that we can think about these formulas in terms of relations. So let's look again at the formula for indirect monotonicity. If we look at the formula on the left, f of x less than z, we can view this as a relation relating x and z. The same way, the formula on the right is also a relation relating x and z. So this if and only if equivalence could be restated as saying that these two relations are equal. Furthermore, the complicated relation on the right can be broken down into simpler relations. It's the composition of the less than or equal relation with the relation f of y less than z. This reveals that this relation f of y less than z actually appears twice in this complete thing because it's the same thing as f of x less than z. The variable names don't actually matter. So to emphasize that the variable names don't matter, we switch to a point-free notation. And not only that, a diagrammatic notation. So we use this diagram of f inside of a little bullet symbol to represent the relation f of x less than f of input less than output. And we use this straight line with an arrow to represent the relation less than or equal. And this whole thing, the whole formula for indirect monotonicity can be restated as an equivalence between the composition of diagrams. And we can continue with this idea and create diagrams for other kinds of useful relations that appear in the kind of proofs that you want to prove. So for example, we have sequential sequencing of two relations, which introduces an existential variable. We also have the predicate that compares against a constant. You can remember that constants are just functions that have a single input, so it's basically the same thing. And we also have diagrams that allow us to bend wires and diagrams that allow us to split wires, so the input variable can be used twice. One thing that all these relations that I'm showing in this slide have in common is that for every single one of them, if you decrease the x or if you increase the y, the relation still holds. This is a kind of this kind of relation is known as a feasibility relation. And one interesting thing about them is that for all of them, this idea of can decrease x and can increase I is the same as saying that if you compose with the less than or equal relation, the result is unchanged. So less than or equal is the identity of composition in this setting. This is why every single diagram you see here, if you stick the diagram for the identity in the end, the diagram is unchanged, right? It's just an arrow line with an arrow in the end. So using these diagrams, you can have nicer ways to draw the complicated formulas you had before. So here's the diagrams for the specification of a least prefixed point. The top diagram states is the predicate y is greater than mu of f. And the middle diagram is the diagram that states there exists some prefix point a that is less than y. You can read this diagram as saying that this inner loop, the Indy track here, is the variable a, and the wire that goes to the end, the loose wire, is the variable y. And the two nodes in the diagram, the f node and the black copy node, they introduce the inequalities f of a less than a and the inequality a less than y. Summing up, if you the original specification that states that f has a least prefix point can be rewritten as an equality between two diagrams, and this equality can be used as part of an equational proof. And let me just show you what this equational proof looks like. So this is a complete proof of the rolling rule, completely equational, fits in a single slide, and doesn't make my eyes bleed. The way this proof works is that all the way on the end, we are equating the predicates that state that y greater than fixed point of f of g if and only if y greater than f applied to fixed point of g of f. And we will do so by rewriting one diagram at a time, step by step. In the very first step, we use the specification from the previous slide to unroll the fixed point f of g and turn it to an unrolled loop. Next, this is the key step of the proof. We use the fact that if you copy the output of a function, it's the same thing as copying its inputs and then applying the function to the copied inputs. So the function can't go through the copy node, and we copy the function when we do so. The next step, we take the innermost f and we push it all the way around the loop, which is allowed because, again, wire is the identity of composition in the setting. And the result is the diagram that represents the fixed point of g of f. So by step-by-step rewriting, we have left from the fixed point of f of g and arrived at f applied to the fixed point of g of f. Clearly, this proof has something going that the previous one didn't, but what? So I would summarize it as follows. First of all, there are no variables here, none of those tons and tons of existential variables, because the notation is point-free. Next, the notation bakes in the composition with less than or equal into the idea of a feasibility relation. So we don't have all those boring steps that only served to move the inequalities a little bit. Many of those formulas in the previous proof, if we converted them into diagrams, they would result in the same diagrams. So effectively, by working at this diagrammatic level, we're skipping over many boring steps. Also, the diagram notation, it helps us give us a hint of where the rewrite opportunities are. It's easier to discover the proof than in the other style. Even though technically we could, it's much easier in this new notation. So, in conclusion, if you enjoyed what you just saw, in this full paper, you will also find more proofs proven in this style. So including my favorite theorem, the fixed point fusion theorem. And we also have a more complete discussion of the graphical axioms we used, as well as some pros and cons we encountered in practice, things that are nice to reason equationally and things that didn't work quite as well. So thank you very much for listening, and we'd be happy to take questions here and on Discord.
Maybe we can get the next speaker to start setting up. We could do one quick question.
Hi, great talk, thank you. So all of the constructions you showed on feasibility relations also work for profunctors, is that right?
Yes, this thing has many names. One of them is Boolean enriched profunctors.
Yeah, so did you think, are there applications where you could use that semantics instead of the relational semantics? Like an actual profunctor semantics, not a Boolean valued profunctor semantics, and reason about fixed points of functors instead of functions.
Hugo, do you want to answer this question?
We have another Hugo, I think in the audience maybe? Or,
Hi. I'm also on the talk.
Hello?
So, and if you can hear me.
Yes, go ahead.
The answer of the question is that is basically work in progress, right? So the Boolean profunctor is this main example we have worked out, and the other ones we are basically starting to look into.
Great, excellent.
There are some technical bugs and technical issues which we still have to work over.
Good. Well, let's thank Hugo and Hugo.
Semiconductor electronics. So right, we have this image in our head of two endpoints and a wire.
and across the wire is a constant voltage, and we can say, put a multimeter on the wire. If it's high, then that is going to be some kind of true, and the inverse of that is no voltage or low voltage, and that's false. So something interesting about this, right, is that the wire is therefore a stateful element. I can always go over and sort of check what its value is. So by contrast, superconductors can be thought of still in this mental image of two endpoints on a wire, but instead of a constant signal, I just have sort of a periodic transient signal. So a single pulse that lasts maybe a picosecond or something long. So a lot of things sort of change immediately. The wire is now stateless. I can't just go over and check what its value is. I needed to have been listening for the pulse. And the gates now have to retain that state. So the timing becomes very important, how these gates remember when they received a pulse, when the last time they received a pulse was. And we lose a connection to Boolean logic the way we used to have, right? It doesn't really make sense to talk about the negation of a pulse. This is a sort of broad category of logics, though. So photonics, if you've heard about that. If you think about EEGs, they take spike train data or neuromorphic data. These are all pulse-based. But from a functional programming perspective, maybe we just think it's cool, novel information encoding. Conceivably, though, this would be efficient because you don't have a constant voltage draw, so you would imagine a huge amount of battery efficiency. But we won't talk about that. Nevertheless, we still have this notion of a gate. So, right, you think about an AND gate in classical electronics. Well, we still have those, and we still want to stitch them together in these larger graphs. So, just have this kind of a picture in your head. For what it's worth, currently, I assume superconductors are still quite an emerging field. So even a large example would be relatively small by CMOS standards, like a sorter network. Building these is a really intensive process. It requires a lot of low-level electronics knowledge. You use a tool like SPICE to make these things. So we would like to come up with a more useful abstraction. It makes it easier to compose and reason about these. So to that end, I tried to make Citrus. It's a DSL in AGDA. So circuits are now going to be functional programs. I'm going to use the richer type system to take advantage of, or to express correctness properties. That means types for pulses, for the circuits, for the equivalence between circuits. And then I'm going to claim that what this means between for two superconductors to be equivalent is going to be most easily expressed using AGDA's co-induction facilities. So ultimately, Citrus is a DSL, and there's a library of components that we think are verified against their actual behavior. So the main component we have to get through. It's conceptually easy to think about a transducer or a Mealy machine. So let's look at this. I'm sitting in init, and I can receive an A pulse. So let's look at that A/1. That means I received an A pulse, and the /1 means I'm outputting. So we have a few more numbers, though. The 50 is going to be a transition delay. So that means it takes me 50 picoseconds, let's say, to get from init to A received. And the 120 would be if I output, which I do because of that /1 notation, it's going to take 120 picoseconds before that is realized, or you see that. And similarly, the /0 would mean I received a B pulse here, but I'm not going to do anything. I'm not going to output. So this is a model of superconductors. In fact, this was a previous model that I worked on. And the issue here is that when you start composing these things, you're obviously making just really big graphs, right? This automata theoretic approach is going to ultimately suffer from kind of a state space explosion problem. It's hard to reason about these enormous graphs. And so to that end, I tried to take a cue from functional reactive programming and say that the basic component now I want is an arrow, right? So for us, an arrow is just going to be a generalized function. It's got input ports and output ports. And the real big win here is that I can compose them in a variety of schemas, right? I can put them in sequence, in parallel, I can loop them. And with that, I now have a lot of the core material I need to start making superconductors. The schematics I saw earlier, I'm going to claim I can do with these arrow combinators. So just to throw in some basic types, I'm going to take a really simplified notion of timing. If I have fractional times, I'll just upscale them. A pulse really is a sort of thing, or it's the absence of the thing. However, I'm going to include this error to make it easier to propagate error signals in my data flow networks. And then I'm just going to combine those, and so the basic unit of input-output in this is going to be a timed pulse. So at a given time step or a timestamp, I also record whether there was a pulse, there wasn't a pulse, or some sort of error signal. So to that end, this picture that we just saw, this basic superconducting gate, is now going to look like a looped arrow, right? So there's going to be the input-output behavior, which we talked about. However, we also need to keep track of what state we're in. So we're going to keep track of whether we're an A received or B received and when I last received a pulse, things like that. So this is going to be two different components. The I/O is going to be these pulses and then the output pulse, so A and B, but one output. It's called FA here because this is a first arrival gate, which I'll describe in a second. That will be relevant. And then the other component is this looping or feedback. So the type of the first thing on the left is going to be this timed pulse that has width 2, and the state vector is what I'm attaching that I'm going to try to feed back. And then it has one output, so timed pulse 1, it has width 1. And then loop is a combinator you get in the arrow calculus, so essentially what I'm going to claim is that all of the useful superconducting gates are a result of using the loop combinator on some I/O function and some feedback state. So I can loop these together. So the thing on the bottom gives me the thing on the top right, and that's going to be all of the basic gates. Those can then be composed, right? So we mentioned that you can compose arrows in parallel and sequence. These are basic combinators, and they get instantiated sort of directly against the pulse gates. And so with that, we now want to think about, well, when are two superconducting gates equivalent? So obviously, we care about equal inputs should be equal outputs. The same sort of input pulse sequence should generate the same output pulse sequence. So from reactive systems, we're going to inherit this idea of bisimilarity. However, of course, that's much too strict. And so I claim that the right set of adjectives is time abstract weak bisimilarity. So what I mean is I'm allowing up to some timing window, arbitrary time delays. They don't need to be lockstep in the same time sequence. And two different circuits can have their own set of internal actions. I don't mind that. However, they should pulse at the same times, or at least in the same order. Another component here is that with a lot of electronics, you don't really think of things terminating, right? These circuits should always be responsive. And moreover, we sort of saw this in the picture, but I'll get to it in a second. There's a kind of fresh state, dirty state cycle that all of the gates should go through. You start in a clean state, something happens, and you need to wait until you can be pushed back to your initial state. So these always-on cyclic behavior gates, I claim, are going to be easier to represent and work with co-inductively. So if you wanted to represent bisimilarity as a co-inductive type, this is a really straightforward way to do this. The idea is that this is a record type tagged co-inductive in the Agda language. So for any two circuits, M1 and M2, I would like to be able to always project out two different components. That their I/O behavior is on the nose equal. I want them to sort of pulse or not pulse or error at the same time. And I want their continuation. So as I'm stepping these forward in time and they're moving through their own internal machinations, I want those to be bisimilar. So I want those continuations to be bisimilar. In the paper, there's a little bit more involved, so we can take care of timing and delay elements. But that's the basic idea. So with that in place now, what is something I could prove? So let's dig slightly deeper. I know this is kind of gnarly looking, but it is symmetric, so we'll just look at the left-hand side really. This is called a first arrival gate, and it is in some sense like a disjunction. So when we look at that, what we mean is that I get an A pulse, right, and I immediately output. I'm stuck in A received until I get the B pulse. And symmetrically, if I go to the right, if I get a B pulse, I output. However, I don't output ever again, but I do have to wait until I get my neighbor pulse. Contrasting this is the last arrival gate, or the AND gate, which looks nearly identical, but the main distinction here is that if I receive that initial A pulse, I'm not going to do anything until I finally get my companion B pulse on that bottom edge. So the first one will sort of output immediately, and the second one has to wait to output before it receives all of its gates. And then they're kind of these weirdo versions of OR and AND because, again, they need to receive all of their inputs before they can cycle back. But they're kind of like OR and AND. So what could we do with that? Well, let's try to prove something from classical Boolean logic. Again, we're claiming that it's not a Boolean system, but what if we just tried? So classically, we know that disjunction distributes over conjunction. So M or A is the same as M or A and B is the same as M or A and M or B. But we have all of those components now. So the disjunction and conjunction now are represented as these gates that I just saw. The M, A, and B are just going to be timed pulse wires, and the equal sign has been replaced by this delayed notion of bisimilarity. So schematically, what you'd write this as in a circuit form looks like this. So the left-hand side is that top circuit. The sort of topmost connective is the disjunction, so it's the FA on the very far right. It's fed by the conjunction, which is now a last arrival gate. And similarly, in the right-hand side, I have two gates in parallel, the M or A and the M or B, and those are going to feed the topmost conjunction connective, which is our last arrival. So the question is, can we prove that these are this bisimilarity notion that we set up? What does this look like in Citrus? This is what we were trying to do. We were trying to write these slightly larger circuits in a really concise way, so we can do that. The Citrus calculus makes this very easy to set this up. So now what we do is we need a proof technique, right? So the strategy is going to be this, right? Taking into account this sort of weird cyclic behavior of superconducting gates, we're going to determine the unique sequences of inputs for each gate that cover their I/O. So I receive an A pulse, then a B pulse, or vice versa, or I receive them at the same time. I'm going to assert a co-inductive hypothesis that captures the resetting behavior, so when I expect to go back to my clean state. I'm going to establish that nothing goes wrong. Essentially, I'm pulsing when I expect to, and then I sufficiently have done everything, and I'm going to employ my co-induction hypothesis. And so that should be my proof strategy. It'll feel a lot like induction. Of course, instead of working towards termination, we're working towards unceasing productivity. So the type of one of these looks like this. So this sequence would be the M sequence, an M pulse followed by an A followed by a B. This would be the co-inductive hypothesis that covers that looping state to go back to fresh. This is just going to be the sequence of things that MAB acts on in the circuit. And then finally, this is what needs to be proved, that the outputs of these three steps are the same, and that the continuations are bisimilar. So with that, this is inhabited very directly. AGDA confirms that indeed these pulse or don't pulse in lockstep fashion, and that indeed the co-inductive hypothesis that we think is the right one does establish that case. So that sort of confirms to us that this does move to a dirty state and then move to a clean state as expected. So the upshot of this would be that we kind of think that, okay, well then superconducting does enjoy a version of this distributive law, which is kind of interesting. I will note one more thing, that this really comes from an optimization that you have in electronics called a retiming law. So this is in some sense an optimization because the thing on the top has one fewer element than the thing on the bottom. So it is kind of also a practical utility. But with that, there's one more advantage that we had. So I mentioned that I worked on a version of this previously that was much more automata theoretic. So that was called Pulse. So in that case, the verification was done by model checking. And so the state space explosion meant that there were a lot of circuits that we couldn't prove correct or equivalent just through explosion. However, Citrus, because it encapsulates state and streamlines composition much more directly, makes these proofs actually doable. So several of the proofs that we couldn't do in the Pulse paper can be done in Citrus very straightforwardly. Granted, they are manual now. You have to do them manually as opposed to push button model checking. The other caveat is that Citrus technically takes a simpler perspective on timing relations. However, I claim that those can be added back in, and that won't change any of the basic results. So in sort of summary, SEE does enjoy a usual version of this distributive law, which is interesting. That's the beginnings of a logic for SEE built on this timing bisimilarity that needed to be figured out and this encoding of localized state for superconductors as arrows. Citrus, first type-driven DSL for reasoning about SEE, and I claim similar pulse-based logics. It establishes behavioral equivalence, verified a larger sorter network that we couldn't previously. It's compositional, has strongly typed components, and because it's used in AGDA, you have a much more interactive process of designing and debugging with it, which is preferable compared to making monolithic automata and then just running push-button checking. So with all of that, I'm happy to answer any questions if there are any.
Thank you, Harlan. Do we have time? One question maybe, and I can get the next speaker to start setting up.
Hi there, Antal Spector-Zabusky from Rigetti Computing. I spend most of my day working on a compiler for superconducting systems, so I am curious if you think this points at any programming models as well as verification models for pulse-based systems or superconducting type systems, or is this just tuned specifically towards verification, which is already a worthy goal?
Yeah, it's a great question. I mean, we should definitely talk later about this because I think, this started maybe slightly more as a verification task, and we were always wondering, like, well, what are some really cool circuits that we could make, right? So, using this much more as an actual design language would be awesome.
Come find me.
Yeah, definitely. Thanks.
Great. Let's thank Harlan again. So next up, we have compositional neurocyberphysical system verification in the interactive theorem prover of your choice. And this will be Alistair giving the talk. Take it away, Alistair. Thank you.
Thank you. So hello. We'll be looking at how we can use functional programming techniques to set up neurocyberphysical system verification. So for a bit of background, I know the keynote yesterday touched on cyberphysical systems as when computers interact with the world. You can sometimes think of these as self-controlling machines. Good examples are autonomous cars. You can also have the cyberphysical systems acting in tandem with a person, like where a pilot may be in the control of the plane, but having some assistance from computerized systems. Another quite interesting use case is in medicine, where you want some computational model to help decide on a dose to give a patient to treat a certain ailment. The patient is then monitored and the dose is re-given. This is what that looks like for the concentration in your blood after taking orally doses of medication. When we're looking at these kind of problems, we generally split them up into two categories. We have finite horizon and infinite horizon properties. Finite horizon properties are ones that have natural endpoints. If you're trying to land a helicopter, at some point it should land, otherwise you've messed up. Whereas an infinite horizon problem should go on indefinitely. And for the medical example here, you really want to be able to treat somebody for an extended period of time in some situations like insulin pumps. When you're dealing with stuff like this, it justifies verification quite strongly because you don't want to give somebody too much insulin, you don't want the helicopter to never land. So there should really be ways to verify this stuff. And it turns out there is. There is this community ArchComp that is set up around finite time horizon verification of both cyberphysical systems and cyberphysical systems with neural components. There are also a series of papers about cyberphysical system verification in infinite time horizon using ITPs, and even an entire thesis about it. However, in the literature, we are only aware of one paper that combines both of these topics, where you are doing neural cyberphysical system verification across an infinite time. And we can get a bit of a better understanding as to why that is by looking at what currently exists in this space. So we can look at the ArchComp community to see finite horizon tools for cyberphysical system verification, something like Flowstar or Cora. You can look at static analyzers where you have SMTs which are highly optimized for doing maths and other things. And you have neural solvers which follow quite similar theory, but are very, very targeted towards finding properties about neural networks. And then for infinite horizon, as we've just seen, we have ITPs. But notably, it is missing for neural networks. There exists links between SMT solvers and ITPs in most of your chosen ITPs. So can we follow the same idea, take a fragment of logic, compile down to SMT solvers, use certificates, raise it back up, and reason about it all in an ITP for neural solvers? Not quite. Neural networks can be very, very large, and although they can be represented in ITPs, these can come with pretty significant performance constraints. Similarly, we believe that when you write your properties about neural networks in an ITP, you should also be able to use it for training. The same computational restrictions apply when it comes to training. It's possible, but it's a lot slower. You'd really want to integrate with PyTorch or similar. A lot of neural networks are deployed on custom hardware, and we're not aware of any convenient pipelines from ITPs to FPGAs or something similar. And even if you overcome all of these problems, you will have done it for just one ITP, and would have to repeat it again across all the current ITPs and any future ones. And ITPs are generally quite hard to understand if you're not a part of the community that works very closely with them, So for the machine learning practitioners who want to be training based on these properties, it can be a very, very high bar versus Python. So what's the solution? We believe a compositional approach should be taken. We think you should split up the reasoning about the neural networks and everything in that world from the symbolic world, the ITP reasoning. Where in the ITP you can reason about some abstract function that has a certain property about it, and you can prove something about the system that it acts in, the world that the system is in, and then find properties of that. And we believe that the neural world should consist of training, finding whether or not this property is true or not. And then these two should be composed together to get your final result. And we propose a tool for that called Vehicle. Vehicle is a DSL written in Haskell. It has some dependent types in it, and it's designed to help bridge the gap and be approachable to everybody, be ITP non-specific as well. Vehicle has three main what we call backends to it, or integrations with other tools. You write a single property about your neural network in Vehicle, and it will automatically be compiled to training, so it can be integrated with training regiments. It also goes to a verification backend. This goes down to the neural solvers we talked about before that will check whether or not these properties hold for the neural networks. And finally, in the focus of this paper, the integration backend. And this is when we take the same property and translate it into the ITP of your choice. So why do all of this? What do we gain from having this computational approach that we couldn't do before? Well, if we look back at the idea of giving somebody a series or an infinite series of medication, it's really desirable to not kill them. So we want to be able to prove that if a neural network's in control, we won't do that. So we want to make sure that we never cause an overdose by exceeding a safe concentration amount. And we can do this using our tool. We start off by defining some pretty basic elements. So we have type aliases and dependently typed tensors for checking. And we use this @network decorator to say that at a future point when a vehicle is invoked through the command line, we will be provided a neural network. This means you can avoid instantiating the entire network in the file, which is not very convenient. In a similar fashion, specification should be generic over certain factors. So we have this @parameter decorator that means that you can provide these parameters at the same time you provide the network. In this case, it's C-safe, which is the maximum safe concentration you can have before you start risking kidney damage or death. This changes from person to person, so the specification should really be generic over it. We then can start looking at what a property looks like. You generally define some input region. In this case, it's what we call a clinically viable patient, and essentially says they're not currently overdosing, they're not on fire or freezing, they have white blood cells, pretty much just that they are alive. And then we can define an output region, similarly, and in this case, that is non-negativity because it doesn't make very much sense to be taking a dose out of a patient. And then we can use a property decorator to pass this on down to the neural solvers to check whether or not this is true. This is quite a basic property, and we can look at a bit more of an interesting one. And we're going to try and find an invariant of this situation that is enough to prove that you never overdose. So this is what happens to your body when you take a single dose of a certain drug, and it's defined as concentration in rock. Similarly, we can look at an infinite series of doses based on this tuple, and see that it jumps up again when you receive a new dose, as you would expect. And we can start thinking about what an inductive argument would look like. So we have this vertical blue dotted line. We're going to assume everything before that is already safe. And we're going to take the baseline concentration at the time your new dose is given, and that's labeled as C. So we're assuming that your concentration will never drop below this point again. We then use Vehicle to model the highest dose the neural network could decide to give you on top of the baseline, which is quite clearly a sound over approximation. And then the problem becomes as simple as testing, is this approximation below this C-safe boundary we put in before? And we label this point D. So then we can go ahead, we can write this in Vehicle. It doesn't look particularly nice because the equations aren't very nice, but this is just as simple as, is C plus D less than C-safe? And we can similarly use the property decorator to pass this down to the neural solvers. So hopefully you all found that satisfying enough for an invariant. Now, how do we prove the invariant is sufficient? Well, in this case, we used ROC. As mentioned before, it links up to other ITPs, so you can have the one of your choice. But here we define that there is some arbitrary function network. We say that there is this non-negativity property about the network. We say there's this safe property about the network. And after 1,000 lines of ROC, we can prove that the total concentration never exceeds this safety boundary. Now, if you're paying attention, you may have noticed that non-neg and safe are exactly what we wrote in vehicle minutes ago. And we can compose vehicle with ROC to fill the holes that are left by these hypotheses. And vehicle will automatically generate these statements for you, so you don't have to copy it across by hand. So this case study was clinically motivated. We looked at the literature from medicine to determine some of the equations. It's an infinite horizon proof with continuous dynamics. It required quite a lot of real analysis, about 1,000 lines of code, 40 lemmas, 50 new definitions, and about 450 unique lemmas from analysis. So how does this work? Well, if we look at the system diagram for vehicle, you'll see that on the left there is the other two backends, the one to do training in Python and the queries for the neural solvers. And on the right, we'll see there's this intermediate ITP language. This language is set up so it is very simple to translate between it and any ITP of your choice, meaning that it only takes a few hundred lines of Haskell to add a support for a new ITP. And interestingly, we reuse the exact same type checker for all backends by simply expanding upon the core language. This is an example of some extracted code to ROC, where you'll see this is the non-negativity output without the cleaning up that I did before. And similarly, if you're paying attention, you'll notice that what started in bool has now ended up in prop. Because the language is designed to be approachable to everybody, we can't expect a user to know prop versus bool and how to decide. So we do that for them. You write everything in the surface language with bool, and we will automatically compute for you through a novel decision procedure what should be translated as bool and what should be translated as prop. So to summarize, are ITPs ready for cyber-physical system verification? Yes, we've seen quite a large body of work, a lot of it in Isabelle Hole. It really is dependent on a lot of these mathematical libraries. Are they ready for neurocyber-physical systems? As we've proven today, yes. With vehicle, you can get the computational scalability of using these highly specialized neural solvers while also being able to reason about the systems abstractly in an ITP. So we described the core language, and we have this novel ITP intermediate language. We integrate with 4 mainstream ITPs and wrote quite a large tensor library for ROC to support it. And we have this infinite time horizon proof of a continuous neuropsychophysical system. Thank you for listening. You can find our GitHub on the left and the paper artifact, which includes the ROC code on the right. Thank you.
We have a bit of time for questions. If anybody would like to ask a question to Alistair. I've got one question for you. So one of the things I find surprising is that it's possible to get strong guarantees out of neural networks. I mean, probably some people here as well as me are kind of not familiar with this aspect of neural network research. And so I was curious if you could say just a little bit about that. Like, how big are these networks and how is it actually possible to verify them?
So the tool that we use here can do up to 14 million parameters at the moment. This was a few years ago, so we think that it's a bit higher now. They essentially work by, in the worst case, they split every activating function into linear over approximations. And then if you do this enough, a neural network is just a bunch of different possible linear transformations. And then you do simplex algorithm on each of these to check the input domain versus the output domain. And if the property holds for each one of these potential paths, it must hold for all of them.
Is it common that these neural networks are just implementing some sort of learned heuristic, and so they're operating within a bound, but you're not sure exactly what the choice is going to be, but you can prove that the bounds hold? That's the key idea?
Yes.
That's very interesting. Yeah. Excellent.
Any questions for Alistair before we move on? All right, let's thank Alistair again. Somehow we've managed to get back on schedule. I don't know how that happens because we started about 5 or 6 minutes late. But so setting up here is Johannes. He's going to tell us about completeness of iris-based program logics. And I'll see if the setup works. All right, all good? All right, let's listen to Johannes. Take it away.
All right. Yeah, thanks for the introduction. This is joint work with all of these awesome people. Yes, today I'm going to talk to you about the completeness of iris-based program logics. And to talk about completeness, I should first maybe explain what is iris, what is a program logic. So here I brought you a program. This program goes ahead and allocates a cell in the heap that contains the number 40. Then it increments it by 2. And then it returns the value that is written in there. And in program verification, we now want to prove some properties about these programs. Usually we write them as like a hot triple. This hot triple you can read as we can always execute this program, and in the end it will return the value 42, and there will also be some heap cell that stores 42. Right, and then usually what we do is we devise some sort of syntactic proof system. In our case, it's iris, and in this we can then write down a syntactic proof. We apply a bunch of rules, we build some sort of proof tree, and then when we have built a proof tree, we like to think we're done. But actually what we want to do is we don't want to build a proof tree, we want to actually establish some property of our program. For example, we want to establish the property that our program is safe, which is usually what we do in iris, where safety means that our program never gets stuck, and if it terminates, this post condition phi holds. But usually, at least in iris, this is a partial property. Our program can also loop forever. Right, this is what we actually want to prove. So this is usually modeled on the operational semantics of our programming language. So to go from our syntactic proof that we build in iris to some fact of the semantics of our programming language, we usually apply the soundness theorem of our logic. Right, this should all be fairly standard, and our completeness is simply going the other way. It is proving that whenever a program is correct, we can verify it in our logic. Right, all correct programs can be verified. This is what we're trying to prove today. And at this point, when I talk to some people about this, they often had one question that I will address immediately, namely, didn't Kurt Gödel tell us some time ago that we can never prove anything complete as long as it is sufficiently expressive? And well, Kurt Gödel was right about certain systems, but in our case, actually, we do not really care about this at all. Because in iris, we can kind of cheat a bit. In iris, we have this pure embedding. It's written with these fancy bars. And the pure embedding allows us to take any metalogical proposition and turn it into an iris thing, an iris proposition. And then in order to, for example, prove in iris that this proposition holds, we're able to fall back to metalogical reasoning. Which means that our proof system is not entirely syntactic. It doesn't really do anything for pure proposition. But what it does do is, of course, it does separation logic, and so it tells us how resources flow through our program and so on and so forth. This is what we usually care about in iris. This is what our proof system captures. And this is also the motivation for our work today. The actual motivation for why you should care about completeness is a bit delicate, so let me try to be precise here. Here is an example rule of our programming language, of our whole logic. It's this rule of our separation logic. This is the load rule. If you have done any separation logic, this should be fairly standard. You can read it as saying that if our location L stores value V, to then load from L, we just know that this works, this is the precondition, and afterwards the value we load will be V, and our heap will be unchanged. And down here, I have the operational semantics rule for loading, and it is very similar. It says that the program load from L will step to the value V, where V is the value that is stored in the heap, and also our heap didn't change. Right, and when you look at them read out like this, I just said very similar things. These two rules are actually very close to each other, which means that our completeness proof in this case, I will do it later, it will be very easy. But not all completeness proofs are easy, because the same whole logic rule here also works in Lambda Rust. Lambda Rust is one of the case studies we applied our proof to. And in Lambda Rust, this is complete for something a lot more complicated than what I showed you above. Because in Lambda Rust, they try to capture data races. And to capture data races, you add a bunch of stuff to your semantics, like administrative redexes and so on and so forth, which means the semantics are very complicated. This rule here is very simple. But we still prove that this rule does not lose any precision. All programs can still be verified with this rule, which means in a sense that this rule is a perfect abstraction of the complicated semantics. And this is the main reason we try to come up with this completeness proof, in order to prove that certain program logic rules that are much nicer than the semantics are perfect abstractions of the semantics. Okay, So to summarize, we are trying to prove completeness of the iris logic, and we have some example language to motivate this. And the iris logic, as mentioned, is some sort of derivation system with this pure embedding. It has separation logic, and it has for triples in order to prove something about programs. And our example language that I just showed you a bit earlier is a bit like OCaml or a bit like the lambda calculus, and notably it has higher order state. And if you have higher order state, it also means you have all sort of funky kinds of recursion. We're not going to get into this much, but just to mention it. And it has a semantics. This will be a contextual operational semantics. I cannot show you the full definition, but I think on Monday there was a talk at PLMW about contextual semantics, so it's kind of like this. Yes. Now what we're trying to prove is this thing there. We're trying to prove the sort triple, where we say that if our expression E is safe, then in the end it terminates with the post condition we promised it would be safe under. But of course we now have to construct this proof using the rules of our logic. Yes, how are we going to go about this? Well, first we're going to look at the rules of our logic. I've shown you some already, but I need to go into a bit more detail because this is really what the completeness proof is about. Then we're going to do the proof. Then we're going to strengthen the proof a bit, and then in the end we will discuss what we've learned. Okay, so let's look at the laws of our program logic first. So to learn these laws, we will just verify this example program I've shown you earlier. We should by now know what it does. And the way we verify this is by, again, applying a bunch of rules. The first rule we want to apply is this rule here. It says that in order to have the allocation, reason just about an allocation, we can always do this, and then in the end we get out a new location and the points to for this location that tells us that this location stores a certain thing. So we would now like to apply this here in our program, since our program starts with an allocation. But we run into a slight technical hurdle, which is that the allocation is not, the program is much more than just the allocation. The allocation is somewhere in this larger program. And to make progress here, we first need to focus in on this allocation before we can continue with the rest of the program. And for this, we have this bind rule here. It's a bit hard to read, but what it says that is in order to verify the program here, where E is in head context, or the head regex, we can first reason about this head regex, and then, once it has evaluated, continue with the rest of the program. And if we combine those two rules, we are indeed able to make progress here. We're able to allocate this points to, and then we just have to have the location here. Then we can continue with the rest of the program. Great. So we've done one step. We can now do many more steps. The next step would be to apply the let rule. I've shown it here. It says that to prove that a program that has a let binding is correct, we can just prove that the program where we do the substitution in is correct. So we can now apply this rule, and now our program looks like this. And you can already kind of see we're trying to symbolically execute the program. And what you also can see is that this is kind of close to how the program would execute operationally, which maybe gives you some intuition for how the proof will work later. But we can go on here. We can now apply the load rule. You've already seen it earlier to execute this load, which just puts the 40 here. We can do it, then do addition. There's a rule for this. At this point, I'm running out of slides, so I just mentioned that the rules exist. But you can kind of imagine it looks a bit like the let rule. We can go on like this. We can do the store, which here's the rule for that, changes the points to here, and so on and so forth. And eventually, we'll have successfully executed our program. And then all that we need to do is we need to show that this post condition here is indeed implied by what remained in the end. And for this, again, there are some rules in our logic that we can now use to reason about the separating conjunction, which requires us to split the context appropriately. Yes, there's a bunch of rules here is the point I'm trying to make. I've shown you some of them. Some of them I don't have the space to show you. What's maybe important is that we can kind of classify the rules into like the language-specific rules, where there's one rule for each kind of thing our program can do. And then there's a bunch of structural rules of the weakest tree that you can always apply independently of what your expression actually looks like. And then there's some assertion logic rules that we can use that are just the standard rules of separation logic when you formalize it. And these are the rules that we try to prove completeness for now. And to do this, we will now get into the proof. And unfortunately, the proof is a bit technical. So if you do get lost during the proof, don't worry. Once the proof is over, I will remind you again. Yes, so let's get into the proof. All right, this is what we're trying to prove. We're trying to prove that if a program is safe, then the post condition holds at the end. And the first thing we need to do is we need to generalize this, because we're going to have to start talking about the state that we're in currently. So we know our program is safe at some specific state, and we will also need to have all the points to that exist for this specific state, so that when we access things in the state, we will have a points to ready. And now what we can do is we can analyze this fact that our program is safe. I gave you some intuitive definition earlier. This here is the actual definition. You don't have to read it all just now. Just know that this is basically a case distinction where either our expression is already a value or our expression is reducible, and whatever it reduces to is also safe. And we will now handle both cases. The first case is the case where it is a value. When it is a value, we also know that it satisfies this post condition already. So we know that if it's a value, it satisfies the post condition. And then we can apply the rules for reasoning about a value, which means we just have to prove the post condition. We already know the post condition holds from earlier, so we're basically done at this point. This case is really not difficult, because we already know we're done with our program. The much more difficult case is the case where our expression actually reduces. Because when our expression reduces, we can again look at the fact that it's safe, and know that being reducible means that there is some successor here. And looking at the definition of reduction behavior, I said earlier it's contextual. So we know that there is some evaluation context and some expression in head context, or in head context that will do a head step here to some successor, and now we have this context to worry about. Yes, again, now we need to again use our safety to know that whatever we step to here will again be safe, because we know that all successors of our current expression are also safe, sort of inductively. So we will know that whatever we step to is safe, and we can update this up here. And now we will have to look at what kind of step our program actually did. So we will do a case distinction on all the possible steps that there are. You can imagine if our program has like 15 different constructs, this is 15 different cases, I will only do one or at most two of them in this talk. The one I will do first is the load case, because it's the most interesting, arguably because it actually uses our separation logic resources. So what do we do if we know what we're doing here is a load? Well, the first thing we have to worry about is, again, that this load is in some sort of context. So we need to apply the bind rule to get rid of this context. And then the next thing we can do is we can realize that because we know that our operational semantics did a store, we know the location is in the heap, and therefore we know that one of those points to here is the correct point to apply the load rule in our separation logic. So we can just do this, and the load rule tells us that we get some value out, and then we can put this into the post condition, and we get it back into our context. And now when we look at this, at the thing we got here very closely, we can notice that this is basically the same thing we were trying to prove earlier. We have some expression here and some state, and we know that this is safe. And therefore, at this point, we're able to conclude our proof, or at least in this case, by induction. Induction on what? Well, for now, let's just say it's induction on steps, but we will get to this later. Okay. There is one other case I need to mention briefly, because something funky happens in there, and that is the case where we have a let binding. Because when you have a let binding, well, you first again apply the bind rule, like earlier, and then you can apply the let rule. But now, because the let rule doesn't leave you with a value, but with an arbitrary expression, you're in this weird state where you still have the context in the post condition, and you kind of want to get the context back out of the post condition to up here in order to make progress. And in fact, we can do this, and it's a bit weird because this is something that is not usually done in Iris, but what we can do is we can apply the bind rule in reverse. Because in Iris, for some reason, the bind rule actually works both ways. This was not a rule we proved. This was a rule that already existed in Iris. It is rarely used, but at this point, we're not going to use it in order to move this here back to something again that again is applicable for the induction hypothesis, which this thing is now. So we can again apply the induction hypothesis because we're back to where we started. And now the proof is done. Great. That was the proof. It got a bit technical. It's now going to get less technical. Okay. We did this proof, perhaps as a summary for those of you that got lost along the way. We started by proving this thing by induction. We analyzed the first step. If it was a value, we were just done. If it was not a value, we then applied the bind rule. Then we did a big case distinction over all sorts of cases. Then in the end, we sometimes applied the inverse bind rule, and then by induction, we were able to complete our proof. So this is the rough outline of the proof. And something you notice when you look at this for long enough is that basically half of this proof doesn't actually depend on our specific language at all. The only things that depend on our language are the things here in purple, and the rest we can kind of split up the proof into the purple parts and the other parts, and then we get a generic framework that you can instantiate with whatever language you already have your Iris logic for, and outfall some conditions that you need to prove in order to establish completeness. And this is basically what we did, and this is how we did all of our case studies, by applying this framework. Okay. At this point, I need to address some loose ends I left in the proof earlier, namely two of them. The first one was that we implicitly assumed our proof was terminating when we did the induction. And the second was that I haven't mentioned concurrency at all, but actually our completeness statement handles concurrency. So the first thing we want to address is non-termination. And as mentioned, our safety proposition says that things are allowed to diverge. And this works because safety is a co-inductive definition. And luckily, it turns out that our Hort triples are also co-inductive. So we can just kind of do the same proof earlier, but where I earlier said we were doing induction, we were actually doing co-induction. And then it magically works. For those of you that know Iris, what we're actually doing here is doing loop induction on the step index, but if you don't know Iris, you can just trust us that it works. The other thing that is a lot more complicated was concurrency. So far, there has always only been one thread. Now, if you imagine there are multiple threads, things become more complicated. We need to share our points to somehow between all the threads. And in order to do this, we will use invariant, which is Iris's feature for sharing things between threads. Specifically, we will use disinvariant. You notice, once again, part of it is generic to everything. One part is purple that you need to figure out yourself for your language. And then we do a bunch more very complicated things that I really do not have the time to get into today. But concurrency was, in fact, the main difficulty when doing this entire proof. So the thing I showed you earlier is quite a simplification. OK, and that completes all the workshopping of the proof we need to do in order to get to our full completeness result. And now we can look at what we actually did with this and reflect on this proof. So we applied our framework, of course, to a bunch of case studies. We applied it to heaplang, which is Iris's example logic. And there we proved total and partial completeness. So basically, by not doing the step indexing co-inductive thing, you also get a total completeness result. And the interesting thing there were prophecies. We also applied it to lambda rust, which is what I mentioned in the introduction, where you have the data races, and we proved the rule complete for the data races. We also have a third one with time credits. Then we also applied it to Eris, which is probabilistic logic. That is built on Iris, but you can't quite use our framework because they had to refactor Iris to add probabilities everywhere. So you need to redo the proof, but the approach we presented still works. You just, for technical reason, cannot apply the theorem we used. All right. And in several of those case studies, we found and fixed small incompletenesses, right? They maybe had a rule that was not quite strong enough, or a case that was missing, or something like this. And we found them, and we fixed them. All right, a second thing I can mention is which features of Iris did we actually need? And one of the interesting features we need is this inverse bind rule. I already mentioned it. We also needed the co-induction thing for non-termination, and we needed first-order invariance and some specific kinds of ghost state, user-defined ghost state in our proof. But many things we did not need that Iris is actually kind of famous for, like impredicative invariance or higher-order ghost state, or the later mechanisms that Iris had come up with in recent times. These we all did not need. OK, and that concludes our proof. We presented the general framework that we applied to a bunch of things. We also applied it to Relog and did some more proofs about the weakest predefinition. You can look them up in the paper. There's some further work that remains about this inverse bind rule, which I would kind of like to get rid of, but haven't managed yet. And there's already some follow-up work that applies our techniques to prove other things in the Iris ecosystem complete. And that's it. Thanks for your attention.
Thank you, Johannes. We have time for questions.
This is really cool. Have you thought about liveness properties, transfinite?
No. I would imagine transfinite Iris is complete for safety, but I don't really know what the adequacy theorem, right? In Iris, you have the soundness theorem. I guess for transfinite Iris, we have some soundness theorem that talks about liveness. I really do not know about this, but we could discuss it later.
Have time for another question, maybe? Anybody has? I have one question. So, I mean, the framework seems quite nice. It seems quite usable. I mean, do you think it would be reasonable, not to over-suggest, but like, should we start expecting, like, soundness is a typical obligation for anything that we develop typically in a paper. I mean, is it reasonable to expect also completeness? Where do you think it would be most significant to kind of expect completeness to be proven?
It usually depends on what the Iris paper is trying. Right? There's lots of Iris papers. They all do various different things. If your Iris paper is about presenting a certain program logic for your language, I would hope that in the future you use completeness. I might be working on such a thing, which is how I came up with all of this, where I hope to prove completeness. But most of the Iris papers nowadays are like about finding a fancy type system or whatever and modeling it in Iris, and their completeness doesn't really make sense because for type systems, this is not something you prove. But yeah, if you present some program logic for some fancy language feature, I would hope you want to prove completeness in the future.
Good. Let's thank Johannes one more time. That ends the session, so we can go get some coffee.
Great. Great, now we can see you. Welcome to ICFP. All right, Tim, take it away, please.
Thanks for having me. I'm presenting HMCFA, a precise and practical big step control flow analysis for effect handlers. And this is work that I did at Brigham Young University for my PhD. So first of all, what is a control flow analysis? As many of you may know, it's a static analysis which accounts for higher order control flow, in particular first class functions and sometimes first class control. It matters for any place where we need to know for certain a sound over approximation of things, and this is especially pertinent for privacy, security, optimization, and can also be used for bug finding and understanding. Some of the challenges that we face when designing control flow analysis is the analysis precision versus cost, especially for complex language features. If you take nothing away from this talk except for this slide and this analogy, then that would be great. The context sensitivity and precise approximations are all related to the language semantics and the language features that we're talking about. So if we imagine a situation where we have an image or like a language feature that produces patterns like this image in image 1, then one approximation that we could do is just split it up into grid cells like in image 2 and kind of take an over approximation of what's in each of those grid cells. And of course, that's not a really great approximation here, but we can always increase context sensitivity, as in image 3 and 4, splitting up our state space into finer grained cells, which produce less leakage in some areas, but we're never going to really get a really precise approximation with that. The ideal is image 5, where we have an approximation that aligns well with the language feature and the language semantics, such that we can cut up our state space in a way that is efficient in providing an approximation. So the next aspect of my talk and the next aspect of this work is effect handlers. This is the language feature that I'm focused on. So effect handlers are a unifying concept for async await, exceptions, generators, and a lot of other higher order control, such as delimited control. The three main aspects of effect handlers are a syntax for handling effects or operations within an effect, and those are represented by this H here, and we insert or we evaluate an expression E that is all evaluated underneath that handler. So the handler delimits the stack. Operations are then able to be called underneath that handler, operations of the effect, which allow us to invoke effects. This is accomplished by unwinding and capturing the stack in a special first-class variable, which I will call resume for the purposes of this talk. Resume then can take a value and restore the stack where value is replacing where the hole in the computation left by the invocation of operation. Continuations are typically what we refer to as these values that capture the state of the computation, where to resume the stack frames, etc. And multi-shot continuations enable probabilistic programming, retry with backoff, and other things like that, where we don't restrict resume to be used in a linear manner. We can use it more than once. So as a quick example, in this code on the right, we have a function G, which invokes operations, and in main, we install a handler for the operations that we're going to use. Here we call resume more than once, so this is going to be a non-deterministic resumption and multiple resumptions. And as you can see on the left-hand side, I like to think of this as a tree, or a where when we hit an operation, we cut off a branch of that tree. And then when we resume, we graft in that branch of the tree again. And this allows us to take whole portions of computations and graph or rebase them into different contexts. In order to abstract these semantics, we first need to reference semantics for concrete semantics. In this case, there's many existing semantics for effect handlers to choose from. There's substitution semantics by Bauer and Pretnar. There's denotational, there's environment semantics. There's also small step semantics. I've worked with many of them, and each of them have their upsides and downsides. And in particular for control flow analysis, we often want to abstract by limiting the domain of the store to a finite number of elements in the store. And so this prompted me to go with an environment and store semantics. And I was able to prove this equivalent to the substitution semantics with a lean-4 theorem prover, at least the subset of the language that is has an equivalence with the substitution semantics from Bauer and Pretnar. And these are both of those semantics on the same slide. As you can tell, my semantics on the left and the bottom are a little bit more complex, and it might look like it's really quite complex, but there's a lot of that is just dealing with extending environments and threading through stores, kind of the normal things that you would do for adding stores and environments into a semantics. The main new thing here is the apply relation, which because we don't collect a continuation syntactically and grow the continuation syntactically, we collect frames instead, and we need to restore those frames when we need to apply that continuation value. And so this is the first aspect of this long piece of work here. Moving on to the next piece, in order to abstract, we need to think about those boundaries or those alignments that will help us precisely capture the language semantics and the language feature that we care about. And in particular, when we abstract, we want to remember where operations came from, where the provenance of the continuation in particular, what context was it that operation in, so that we can resume exactly at that same context. Similar thing with handlers. We want to understand where those handlers were inserted in the stack, what context they were, what other handlers they had available to them. And then the third challenge is continuation fragmentation. Since we have multiple continuations in the store and we're going to keep track of them in the store, we don't want different fragments of different continuations being matched in calls and returns, which would ruin our precision. It would cause the blurred over approximation in control flow, which will leak into the value of the flow as well. So in order to address these problems and these challenges, I came up with an address space, and in particular a sensitivity, a two-component timestamp, to give us the kind of sensitivity that I believe addresses all these challenges. The first part is the continuation timestamp, and this tracks calls below the most recent handler. The second component is the meta-continuation timestamp, and this tracks handlers and continuation context at each handler level. And then the final component is the continuation address space, which not only allocates continuation frames or stack frames at their context in which the stack frame was originally evaluated, but also it keeps track of when that frame was captured and the context in which it was captured, to keep the different segments of the continuation together as a cohesive unit in the address space. So using this timestamp, we can look at the original evaluation and see how the timestamp evolves. And as you can see, it mimics that same tree structure, or the stack and the meta stack of evaluation. And it does it in a very concise manner where we're just keeping track of the control points by these labels in the control points. And this allows us to keep all of these different evaluation segments separate in between control points. The semantics do change quite a bit here, but I've highlighted the important parts in the paper in green and blue. So green is the addition of the timestamps, and blue is the addition to address spaces, and in particular, allocating continuations in the store. Of course, we want to know what are the meta-theoretic properties about this, and we have completeness and soundness with respect to the concrete evaluation. And this is very surprising, maybe, but very intentional on my end, where the timestamp is intended to include all possible behaviors of the concrete program, and that we can represent all concrete evaluations in the timestamp program, because all of the control points are distinguished by a particular sequence of labels and sequence of and particular timestamp. And this means that we don't need freshness by construction or a way of allocating fresh addresses. We can just use the timestamps as fresh addresses, even for concrete evaluation. And in order to prove this, I had to actually add in another fresh guarded semantics. This is a proof device that bridges that gap between the fully time-stamped world and the concrete world where addresses are in the store are assumed fresh by construction of the rules. And so this just bridges that gap. Now, going on to abstraction, we use the typical techniques in control flow literature of limiting the length of the timestamps. And here we limit the length of the continuation timestamp to n, reminiscent of MCFA by Might et al. And we limit the length of the meta-continuation timestamp to a length of h. And then additionally, we have in red the union operators. Because we have limited the timestamps, we do end up with the over-approximation. We have to put things together in the same bucket, and so we union them together in sets, and then non-deterministically access the store. For the abstract meta-theoretic properties, we have soundness, that abstract evaluation includes all possible behaviors of the concrete program, and this is just another step on this chain of proofs. Fortunately, as presented, that abstract semantics is rather computationally complex, and it's due to the environments in which the free variables are stored, because each free variable in a normal environment extension has its own timestamp, or the provenance of where that free variable was original. And the work that I already mentioned, MCFA by Might et al., includes a rebinding operator. And so this is the other component of the puzzle, where we can make control flow analysis a little cheaper. And instead of recording the environment as a map of variables to their provenance or their timestamp in which they were born, we rebind all free variables from that timestamp that we're coming from to the new timestamp that we are creating when we're entering any control flow segment. And so this extends the Might et al. Version, which is just the control segments are just lambda calls, but this is there's several places where we need to rebind here because we are changing control segments frequently. Of course, I would love to say that it's really cheap, but the main win here is that we can get a polynomial analysis, which is not there's no previous polynomial analysis for any sort of higher order control flow delimited control in a big step framework, and many small step frameworks for a good precise analysis do not support these sorts of constructs in a without going through some sort of CPS. And so this is all in terms of T, which is a complex combination of the M and H parameters of the analysis. And H is the first value in this tuple on the top, so you can see what it is for various levels of H and M. Evaluation. For an empirical evaluation, I measured the precision on a bunch of benchmark programs and the relative imprecision recovery, which I define here as the amount of precision we gain compared to a 0 CFA or a CFA where there's no context sensitivity at all. In the results, we found that our approach did really well, and even compared to our same approach with the same address space but with different timestamp strategy using a KCFA-like timestamp strategy. KCFA starts getting timeouts at 2 KCFA, but we're able to go to higher levels of HMCFA without a problem and do really well in precision. In the evaluation, we also have a couple other graphs. Here is a graph of that imprecision recovery across different benchmarks. So you can see that there's a variety of different benchmarks, micro benchmarks and larger benchmarks. We do consistently well across all those benchmarks. With the 2 KCFA, you can see the timeouts for the various different benchmark sets. As soon as you get to a complex benchmark, it tends to get really expensive really quickly. And the next evaluation metric that I wanted to look at was precision versus cost. So you might think, oh, it's really precise, but is that going to be a lot longer of analysis time? And in most cases, we were able to show that it's a pretty good win-win trade-off where whenever we increase precision, we also decrease analysis time, but often we will have a little bit of a trade-off of a slight increase in analysis time compared to a 1 KCFA, which was our baseline since it had no timeouts. So in summary, the contributions of this work are a new big step semantics for effect handlers, a novel timestamp sensitivity that models stacks and metastacks, proofs of correctness in Lane 4, and an empirical evaluation for COCO sample programs. For future work, I have a prototype of optimization for effect handlers and delimited control. This includes dead continuation elimination and continuation join point inlining. I'd also be interested in looking in static virtual operation dispatch, where we can inline an operation call if it is tail resumptive. And also would be interested in interesting future work directions include modular analysis and scaling up to larger programs, seeing if what kinds of levels of sensitivity that we can do for larger programs and whether we need some sort of selective context sensitivity to enable that. And open for questions. Thanks.
Okay, so we've got time for one quick question while the next speaker gets set up.
Hello, I was wondering if you could go back over again what precision is, and particularly the first table where you show percentages of precision.
You know what, I think we better take this question offline because we need to
Okay, yeah.
change the laptop over.
Yeah.
Actually, take the question online to Discord.
Okay, great.
Thanks
Yes,
again, Tim.
Perfect. Thanks.
Next talk is by Stefano. When types intersect and effects get handled.
Okay. Thank you for the introduction, and I'm presenting this joint work with Ugo Dallago and Taro Sekiyama. So what we study is, in general, model checking in this work. So model checking in general is a very used verification technique for programs. So in general, the program has this problem has two inputs. One is a program T, and the other one is a property that we want to decide if this program satisfies this property phi. So in the higher order version of this problem, the programs are specified as H order recursion scheme or PCF terms, and the property can be expressed as MSO formulas or alternating parity tree automatas and other version. So this property can express things like liveness, safety, and reachability. And one important theorem in this work is that the OMC problem is decidable for PCF with finite data types. So in this work, we actually restrict our study to only a subclass of the general higher order model checking problems, that is the reachability problem. So given a term T and a value S, we want to decide if it's true that T reduces to S. And this is a very simple specification, but it's already hard enough to be undecidable in various extensions of PCF, like, for example, probabilistic choice, PCF with references, and with some kind of effect handlers. And that's exactly what we want to study. So this reachability problem in the context of a language with effect handlers. So in general, effect handlers are mechanisms to structure program with effects in a modular way and enabling the user to define their own effects. And we can, with this language with algebraic effect and effect handlers, can represent various forms of effects like exception, I/O concurrency, and many others. So the starting point of our work was this language HE-PCF, that is a call-by-value finitary PCF with effect handlers that was presented in this work by Dallago and Ghislaine. And this language has these terms sigma here that represent an effect that has to be thrown. And furthermore, each effect has an argument V and a continuation T that takes an input, an argument Y. We also have this return, this special return effect that just represent a term that returns the value V, and these effects can be handled with this constructor with handle. And the handlers themselves are represented as a set of clauses. Each clause handle a specific effect sigma have its own continuation that represents in some way the implementation of the handler. So in HE-PCF, the type system is like this. For each type of a computation is indexed by a set of effects. And so a type like this not only represents the type of the return of the computation, but also all the possible effects that we can throw during this computation. So from this article, I know that the OMC problem in general, so also the reachability problem that we're interested in, is undecidable in this language. And the main idea is that handlers can encode natural numbers, and being an infinite data types, this in some way breaks the decidability. This decidability can be recovered by restricting to fragments of HE-PCF, so for example, taking only the resumptive handlers. And also a lot of work has been done to create some variant on this system based on answer type modification.
But all these works use basically a CPS transformation into finitary PCF that is known to be decidable, as I told you before. We wanted to take another look at this problem, so we wanted to use another technique that is widely used in the literature to study the decidability for higher order model checking, and in particular, it's the technique that is used to prove the decidability for finitary PCF. And so this technique is based on intersection types. So for example, if we look at this term here, it's of course not typable in a normal simple type system, because the identity will be fed once with the argument 3 and another time with the argument false. Intersection types give us the ability to type terms with sets of type. So for example, here we can type this identity as an identity on the integer type 3 and as an identity on the Boolean false. In the context of finitary PCF, what we have is that if a term reduces into an integer value m, if and only if it is typable in an intersection type system with exactly the integer type m. And this allows us to reduce reducibility into a typability problem, because if we want to decide, given t and value m, if t reaches m, we just have to find the right intersection type derivation for this value. Of course, the type inference for the general intersection type system is undecidable because, of course, it characterizes the normalization. So what is done in general in this approach is to restrict the search of such intersection type derivation to refinements of simple type derivation. So one can take a simple type derivation and only look at the intersection type derivation that strictly follows the behavior, the structure of the simple type 1. So if one is able to prove that for a certain simple type system, the set of possible intersection type refinement derivation is finite, then one can just exhaust the search of this intersection type derivation and the reachability problem becomes decidable. So this is the general idea of this approach. We have to now apply to our language with effect handlers. So the first thing is to design an intersection type system for effect handlers. This is the first contribution of our work. So if we look at the operational semantic of this language, we have that if we want to handle this effect sigma with this effect handler, the first thing is that we pass the control to the continuation of the effect handler, and then we replace x with the argument of the effect, and we replace r with the functionalization of the continuation of the effect. So we end up with something like this, and as you can see, here we have that this continuation is used twice, once with an argument 4 and once with an argument 5. So in our type system, this term sigma here will have a type of this shape, and this type has an intersection type spirit, if you want. So it represents the set of all the possible, of all the usages that we have done of the continuation of the effect. And it has also a behavioral nature, since we also index each one of these type with the effect that a term gives rise to. So for example, here, this effect is indexed by this effect sigma, and also by the type of its argument in this case tree. So this allows us to have a type system that exactly characterizes the computation tree of our terms. So for example, this tree here represents the type of a term that first uses its effect sigma with an argument 3, then uses its continuation twice, once with an argument 3, once with an argument false, and then continues one continuation length sigma and the other one tau, and so on. So this is just to show you that to have an idea of the grammar of the types, you see that we have this set, so this intersection type system, both at the level of value types and of computation types. And with this type system, we can prove a property similar to the one I showed you before. So the fact that if a term T reduces to the normal form return n, if and only if this term is typable with this special effect return n. Okay, so this is what allows us, as before, to move the reachability problem to a typability one in this system. Now, what we did was also, now that we have described this intersection type system with this behavioral nature, we want to extract a simple type system from it. And what we did was just to, in some way, make the system monomorphic, so we lose all the set in the grammar of types. And what we have is that the types will now be described a simple line, and it describes the exact sequence in which the term has to use the effects and also all the type of the arguments. So this simple type system that we designed has finite data types and is behavioral in the sense that I just explained, and in some ways is also a kind of polymorphism of effects, because here, if we imagine that this sigma and this delta here are actually the same effect, we can describe different usages of the same effect, but potentially with different types in both the argument of the effect and of the continuation. So we can finally prove in this system that given a simple type derivation in this simple type system that we design HEB, the number of refinements are actually finite. So for the same reason that I told you before, we can just exhaust these all the intersection depth derivation that refine the simple type one, and the reachability for this system becomes decidable. So to wrap up, what we did is first of all, to design an intersection type system for a language with effect handlers. Then we derived from it a simple type system, and we proved the decidability of the reachability problem from this system. What we want to do next is, first of all, to add recursive behavioral type to the system to enrich its expressiveness. Then to study its relation with the session types that it's already been hinted at in some work, this connection between effect handler and session types. And since we have this behavioral system, we can hope to explore this connection. And most of all, we want to use this intersection type system that we design to study other decidable and indecidable variants of APCF, because also another important result that we had in the article is that for the HEPCF, so that system that was undecidable, the finite refinement problem actually does not hold. So we hope to be able to follow this same approach to other version of this language, to study the boundary between decidability and undecidability for such problem for other language with effect handlers. And that's it. Thank you.
Questions? Oh, could you sketch a bit about how this would work with session types? What do you think the types you would need might be?
Yeah, this is still a work in progress, so I don't have a specific direction right now. But yeah, the fact is that already the connection with effect handlers have been studied in various other works. So we hope to follow up these directions to study this connection.
Yeah, one thing I thought that was interesting during the talk, it's not really a question, but that you've got one type for the return, right? One value, return M, but then you have a set down below for the intersection to talk about the different effects, because there could be multiple effects, but there's only one return value. Right? But there's one thing at the top and multiple things.
For this? No.
Can you go to a type judgment? Anyway, that worked.
No, what, sorry?
The theorem worked. Yes.
Ah, yeah, okay, this one.
On the right-hand side of the colon, there's one thing in the superscript to say return M, that's one value. But then there could be a set of things in the intersection type there for the effects.
You know, this is because we are interested only in the normal form that are the return, n.
Yeah, no, it makes perfect sense for the context. I'm just wondering how it might change going to a different setting. But it's to be seen, future work, yeah.
Yeah, exactly.
Okay, if there's no other questions, let's thank the speaker. Okay, next talk we hear about demand-on-demand control flow analysis.
Good afternoon, everyone. My name is Chahyun Kang, and this talk is about demand-on-demand control flow analysis and how it improves both the precision and the cost of control flow analysis. So control flow analysis is an analysis method that is necessary to analyze higher-order language features, such as first-class function, but it has a fundamental problem. First, CFA is not that scalable, and second, CFA is frequently imprecise. And let me demonstrate both problems with some examples. Before we jump into the example, just want to do a quick recap on what control flow analysis does. The heart of control flow analysis is a circular dependency. To run the data flow analysis, you need the control flow graph, and to build the control flow graph, you need a data flow analysis because first-class functions are treated as a value that can be passed around. So for example, in this program, there's a simple lambda that takes a g and then applies it with 1. And at the syntax level, we simply do not know what function is being called there with just that program. So when we try to expand it as a control flow graph, we're lost. We can't extend it any further. So we need a data flow analysis to know what G might be so that we can populate the graph further, which explains the circular dependency. So CFA runs this whole circular process simultaneously. So here's a simple example program on the left. It's an ID function that is bound to f in a let expression, and it sequentially applies the f to two different arguments, 10 and 12. And on the right is the state space with a store which tracks the bindings and values in the analysis, and the bottom is just where we're at in the analysis. So to analyze this program, CFA starts from the top like a typical interpreter. And with a let expression, we first evaluate the bound expression, which is an ID function, and we bind it to f. We record it in the store. So once the binding is made in the store, we evaluate the first call site, which is f of 10. And to do that, we first evaluate the operator, which is f, which is a straight forward lookup on the store since it's a reference, which returns the ID function. And then we evaluate the argument and binds it to x. And then we enter the body of that lambda ID function, which is an x. So we do a quick lookup, and the store returns 10. So the result for f of 10 is 10. Now we move on to the next call site, which is f of 12, and we do the same thing where we evaluate the operator first, same function, and then we evaluate the argument, which is 12 this time. But here's the issue where when we try to bind the argument again, the entry for x pre-exists in the store, so there's a data merge within the store. So now x points to both 10 and 12. So when we do a lookup for x, the result is both 10 and 12. So even this kind of a simple let expression program, CFA fails to be precise. So, but now what if we say that that example program we've been talking about was part of a much bigger program on the left side right there? Then the analysis now has to start from the top and has to evaluate every reachable point, which makes the store bigger, doing more work. And at the end of all of that, the answer for the program point that we were caring about is still the same 10 and 12. So now we have paid for the whole program to get the same results. So this approach simply does not scale very well as the program gets bigger and bigger. So the issue that we identify is the pricing model, where CFA runs on what we call an exhaustive pricing model, which it always pays for the whole program, regardless of what we want from the analysis. So here is the whole analysis state space expressed in the form of a graph for that bigger program from the last slide. And the highlighted part is the state space you actually only need to answer our specific query that we care about. So to know about one specific point of a program, you have to analyze the whole program. And like I said before, it becomes quite expensive real quickly as this program gets bigger and bigger. Alternative approach to that exhaustive pricing model, the works have been done applying what we call the demand-driven pricing model to these analysis methods. The philosophy of demand-driven pricing model is that single query should only pay for the information necessary to answer that specific query instead of the whole program analysis. So the framework known as demand CFA is one of the significant efforts on CFA with demand-driven pricing model. So it gets the pricing model right, being demand-driven, but it still suffers from imprecision. And let me demonstrate that with the same example program. So here's the same example program on the left, where now the program point of our interest is zoomed in from that bigger program that we discussed before. And as a note, the middle column is the analysis state, and the right column is the formalism for demand CFA as a reference of what is happening within the analysis. So first, demand CFA can now start the analysis of the expression from where we're interested in, which is the call site f of 12. So what it does is first it evaluates the operator, but here is the issue where it keeps no explicit store to track the bindings and values like the exhaustive pricing model CFA did. So you have to do an additional search to resolve that unknown variable. So it searches for where f is bound, which is the let expression on the top. And once the bound expression is found, it is evaluated. So now the lambda is found, so the body is evaluated. And here's another issue again, where nothing is being recorded about the argument at the call site that we came from. So the analysis is technically argument agnostic. So since the body is a variable from the body, now it has to run the search all over again, just like f. So it finds out that it's bound to the lambda, the ID function, and it's right there at the lambda. And since what binds x is a lambda, the analysis needs to know where the lambda is applied in order to find the argument for that x. So we call that query in demand CFA literature a trace query. So to trace the lambda out, we search for every occurrence where f is applied, since the lambda is bound to f via let expression. So we find that there are two call sites using f as the operator for the function call, and we look at the arguments, which are both 10 and 12, so the result is both 10 and 12 again. So we definitely cut the cost drastically by staying within that necessary scope, like we explained in the demand-driven pricing model, but the result is still imprecise, so this is not quite desirable. So this is where our work comes in. We're solving this problem in both exhaustive CFA and demand CFA, where what we do is we find the middle ground between these two methods, where first we take the store from the exhaustive side and we take the backward search from the demand-driven side. So we call this framework demand-on-demand control flow analysis, or DOD CFA as we'll call so forth. And the result is a control flow analysis framework running on a demand-driven pricing model with great precision. So let me demonstrate DOD CFA with the same setup as before. So before we start at the analysis of f of 12, we first note that we have to pre-allocate every bindings that are in scope when we're starting the analysis there. So in the store right now, we allocated for the F because we passed by the F through the let expression, and all the other bindings via the let reg expression entering there. And first, now we're starting from the application side again, where we evaluate for the operator first, which is a straightforward lookup on the store, which we obtain the ID function. Then we enter the body of the lambda function, just like the demand CFA, but it allocates the argument as a thunk for the parameter variable x. So in the store, x now points to 12. Then when the analysis evaluates x, it just does a lookup on the store and retrieves 12, which is evaluated to become the result. So because we memoized the argument, the analysis skipped every redundant step demand CFA took to evaluate a reference that could have been known from the call site context. So now with the addition of the store, the semantics of DoD CFA now stays a lot closer and close enough to exhaustive CFA so that existing techniques built for exhaustive CFA can be straightforwardly applied in DoD CFA setting. So let's explore one application case of DoD CFA that we did for our work. So the application, the domain, is justifying inlining safety in a higher order language. As a note, inlining is quite straightforward in first order settings, since you only need to look up the definition because usually functions are defined on the top level definitions. In the higher order setting, it is a lot more complicated than that for two reasons. First, each operator can be a different function in different instances, and you need to ensure that only a single function flows there for every instances. And second, a first-class function captures its own environment, and that environment may hold different bindings and disagree with the environment at the call site. This is what Shivers called the environment problem in his dissertation, and let me demonstrate for those who are not familiar with environment problem. And here is a classic example of demonstrating the environment problem. And say we want to know on the program on the left whether a highlighted call site H is safe to inline. So when we run a CFA on it, we quickly learn that the only closure flowing there is a lambda with x, thunk capturing the x. So it appears safe to inline. But when we look closely, we see that the closure flowing to H has a different binding of x compared to what call site does. So in the closure, x points to 42, while at the call site, x points to 0. So this is not safe, and when we do attempt an inlining, that will change the meaning of the program. So one of the framework that effectively solves this environment problem is known as abstract counting, which has been known and been in the literature for a while. The intuition for those who are unfamiliar is that analysis abstract address represents some number of runtime bindings, which can be tracked counting them by 0, 1, and infinity, where infinity stands for any number greater than 1. Now the count gets bumped on every fresh allocation. And if the count is exactly 1, then two variables having the same binding to that specific address must alias, which ensures inline safety when we're comparing two different environments. So abstract counting has been known, and it's been in the literature for a while, and now DoD CFA has a store, unlike demand CFA, so we can incorporate it without much difficulty. So that is what we measure as our evaluation, where we're comparing between our framework, DoD CFA, with the state-of-the-art CFA framework, which is the general KCFA framework. The metric we measure per program is two numbers. One is configuration explored, which is just represent one state the analysis visits, or the one dot on the tree that or the graph that we saw previously, which measures the amount of work done in an analysis, which we use it as a metric for scalability. And so the lower is better. And inlineable call sites detected, which is a metric for precision, how precise the analysis is to detect those call sites to be safe. So we run them both in call site insensitive and call site sensitive settings. And for benchmark programs, we use a subset of ARC6RS suite, plus a suite of 5 larger programs, all side effect free, since our framework cannot analyze effects at the moment, which we'll discuss later. And we set the timeout to 1 hour. And for KCFA, we measure configurations and liable call sites from a single run over a whole program, while for DoD CFA, we measure the same by running a separate analysis at each call site of a program, summing them up later at the end of all the analysis. So the benchmark result is shown in the chart, bar chart there. And as a quick note, we observed that KCFA times out for bigger programs as expected, while DoD CFA finished them in minimal time. And over the program, finished under both KCFA and DoD CFA, we saw an average 86 to 91% decrease in configuration explored. And we also saw an average 13 to 28% more unlineable call sites detected, which is a huge boost in scalability and also some boost on precision too. We also note that across every benchmark and both sensitivity setting, the call sites DoD CFA proofs to be safe are a strict superset of one's KCFA proofs. And for the suite of larger programs, as another note, KCFA timed out on all of them with the 1 hour timeout, and while DoD CFA finished every one of them under reasonable work, and while finding a reasonable amount of call sites, competitive amount of call sites, and extensive results can be found in the paper. So as a conclusion, we present our work, demand-on-demand control flow analysis, which takes the best from the both world, from the exhaustive world and the demand-driven world. And the result is a control flow analysis framework that is significantly cheaper than the state-of-the-art while increasing the precision too. And as for future work, we have mentioned that DoD CFA is currently incapable of analyzing effects, and that is our next target, and since the mainstream languages are typically both higher order and effectful. And that's pretty much it, and thank you, and I'll take questions.
We have about 3 minutes for questions. I was confused. What exactly is the store in DDO CFA? So you're not using the letter K anymore, so I imagine it's a different store than KCFA.
What do you mean by K?
It was KCFA in the chart and
right.
DDO
So
CFA.
for KCFA, K is the timestamp.
Yeah.
And for DoD CFA, I didn't get too into it, but we use the timestamp of MCFA, which is the last N stack frame, instead of last K call sites. So the timestamp mechanism differs a little bit.
Yeah. Well, I'd like to ask for an example, but I'll take that offline.
Okay.
Yes. Yes, so you gave a demonstration of determining whether something is safe to inline based on available knowledge of all the call sites. Is that right?
Correct.
Do you have a way, do you have to sort of pre-process all of that to know that you have all of the call sites? Do you presume whole program analysis, or do you detect if, say, your function is a part of an export in a module where you don't get to control all the inputs? How do you cut that off?
For our benchmark, we used programs that are generally all safe to inline. There's no tricky patterns. So from that, we knew that all of the call sites are safe to inline. So that's where we based on for our benchmark results. I don't know if that answered your question.
I think it does. And then a second question is this just as efficient if I selected all possible call sites and I wanted all the exact same answers as I would have got from a whole program analysis, or is there some overheads involved here?
So when we're just narrowing down our analysis target to call site, that's significantly small subset of a whole sub-expression of the program. So with that really reduces the cost, because we're not evaluating any expression or program part that we're not interested in or doesn't affect or influence our results. So one reason why this is so fast is because it narrows down the target of the analysis drastically compared to the whole program analysis. And because we're just targeting the call sites and the benchmark, that's why there's a huge boost narrowing down of the analysis target.
Right. I understand that, but I mean, if I were using this and then decided that I wanted to grab all call sites of all the functions and do some kind of analysis with everything, is there some kind of overhead involved in this technique where it would have just been faster for me to use the more traditional approach?
I think it depends on programs, because from our experience, for a certain program, like we've done the whole program analysis like by analyzing every sub-expression in a program. And for some program, it's quite faster since there's no like a merge of the data altogether, because like limited to that specific target that we care about. For some other programs, it did a lot worse than the whole program analysis. For example, I think like the satisfiability.
Let's move on to the next question.
Yeah.
Okay, thank you. Let's do John.
Yes. Can you explain what your 0 CFA baseline is? Because the performance numbers look really quite poor compared to other published 0 CFA numbers.
0 CFA simply is, I mean, it's a call size insensitive.
I know the analysis. I'm curious about your particular implementation.
Right,
because
right.
The idea, I mean, those benchmarks look like they should have all taken significant, about 10 milliseconds to analyze.
Right. One reason why it took so much longer is that our implementation for KCFA is a path-sensitive one, where per configuration there's a store, which blows it more, because DoD CFA is also path-sensitive. So fair comparison.
Okay, let's thank the speaker. Okay, now for the fourth talk of the session, Kazuki, you're good to go? All right, take it away.
Hi, I'm Kazuki Watanabe. So today I'd like to talk about our work on adequacy for predicate transformer semantics. So let me introduce the motivations. So what we are working on is the verification of higher order programs. And for instance, we are interested in cost analysis of higher order probabilistic programs with unbounded recursion. And for instance, given a program and its total expected cost is given as expected cost over all executions. And for instance, for this program, it terminates immediately with probability 2/3. And on the other hand, it raises a cost, it incurs a cost 1 and recursively call itself with probability 1/3. And clearly, there are two algebraic operations in this program. One is a probabilistic branching, and the second is a tick operator, which actually incurs the cost 1. And its total expected cost is defined as the expectations of the cost over all executions. And there are a couple of verification problems related to this total expected cost property. And a common verification problem is about a threshold problem, like proving that given threshold bounds the total expected cost from above. And in fact, there is an existing approach to automated reasoning for the expected cost. And this is like an overview of the approach. And we first take the probabilistic programs and the threshold as an input. And then we first apply a CPS transformations for expected cost analysis. And then we obtain a CPS transformed program, and we keep using the threshold. And then by using the dependent refinement type systems, we can reduce the original problem to the type checking problem on the dependent refinement type systems. And the nice thing here is that there is an existing automated solver, mu-bar QFL. And this is based on the CHC solvings, and we can do type checking in an automated manner. And the target of our paper is about the first part, about CPS transformations, and we provide some analysis on this step. So it's closely related to the CPS transformations. And as a background, to ensure the correctness of this approach, the adequacy of CPS transformation for cost analysis plays a very important role. So again, as an input, we have probabilistic programs, and by applying CPS transformations, we obtain the transformed programs. And the adequacy theorem states the following. So given a closed probabilistic program, we have the following equality, which says the interpretation of the transformed programs is equal to its total expected cost, which is defined as in the operational semantics. And therefore, this adequacy connects the two different worlds. One is about the denotation, which is actually computed or like supported by the automated solver. On the other hand, the total expected cost is defined operationally over the transition systems. And adequacy theorem connects these two worlds. And subsequently, Kura and Unno generalized this point of view for a variety of programs in a unified way by using the categorical framework. And in their framework, the source program is now effector program parameterized by a monad and algebraic operations and Eilenberg-Muller algebras. And by applying the generalized CPS transformation, we can also obtain a CPS transformed program. And to ensure the correctness of this approach, they rely on the following correctness theorem, which informally states the following. So given an effector program, we have the following equality. And the left-hand side is just interpretation of the CPS transformed program as before. But the right-hand side is also denotational. So it's basically the composition of the Eilenberg-Muller algebras and post-conditions and the interpretation of the source program. And there, the two sides of the equality is defined denotationally. And the right-hand side is actually also called predicate transformer semantics for imperative programs, and they lift this approach for the higher order computation to support automated verification methods. And this actually leads our research question about adequacy of predicate transformer semantics. What we have an interest is the following questions. So how can we state the following equality for a variety of problems in a formal and unified manner? The left-hand side basically just states the property we want to verify, and this should be equal to the predicate transformer semantics. And the target properties includes the reachability probabilities, total expected cost moments, conditional expectations, reachability, and stateful computations. And we want to cover this property in a unified way. And as an outcome, we can obtain an operational view of what Kura and Unno's approach, where the approach is based on the denotational point of view. So we hope that we can provide some more intuitive understanding or like understanding based on the transition systems. And we also remark that it's not that trivial even for the total expected cost as pointed out as existing research. Okay, so let me introduce our setting. So as a syntax, we employ a PCF with finite-arity algebraic operations following the Plotkin and Powers work. And the type is also pretty standard. It has natural numbers, booleans, and products and functions. And as a typing rule, the typing rule is also standard, and we have rules for the algebraic operations and also recursion. And to define our semantics, we rely on the big step operational semantics. And let's see how it looks like for the examples. So this is a program I showed before, and let's denote L as the recursive term. And then the big step semantics produce this kind of tree, which might be actually potentially infinite because we have a recursions. And suppose we start from M, then we first do some small step executions. And then once we reach to the algebraic operations, we have the transition whose label is associated with these algebraic operations. And it continues by basically once we reach the algebraic operations. And in this way, for each well-typed cross program, it induces a potentially infinite trees. And on top of this definition, we provide the weakest precondition in our framework. So we assume the following data. So a well-typed cross program and a model, which is actually domain theoretic model because we support recursions, and Eilenberg-Muir algebras, and post conditions. And then we define its weakest precondition as the join of the sequence, and the sequence is defined inductively, and it may probably look not that intuitive, but the intuition is that we define the property over the program which runs only executes n step, and we define the property for such a bounded term, and we take the join of the property. And we will see how it looks like for the concrete example. So as an example, we show weakest precondition for total expected cost. And as a model, we use the category of DCPOs. And as a monad, we use a composite monad of the minimal probability variation monad and also the lighter monad for the cost analysis. And as an Eilenberg-Muir algebra, which is actually required to define the semantics, it's designed for the precisely the total expected cost analysis. And the intuition is that it takes two arguments, and one is about sub-distribution over outputs, and the second is the cost accumulated so far during the computations. And then the Eilenberg-Muir algebra computes the summation of this, and here it's again the cost accumulated so far, which is given as a second argument. And it takes the summation with this part, and this is actually computing the expected cost of the remaining computation or like future computations. And as a remark, at least there are two monads which have been known in the literature for the expected cost analysis, but actually they are fundamentally different. And for the total expected cost analysis, only the former monad is appropriate. Therefore, we employ the former monad. And then let's look at the example. So we have this program which have been used several times in this talk, and then let denote L as this recursive term. And also we need to specify the post conditions. And for now, like let's use a post condition which is a constant, which always return 0. And then its total expected cost is actually defined by the supremum of the following sequence. And in fact, this sequence is basically computing the total expected cost for the bounded program. Like the bounded meaning that it terminates in n-step executions. And in this way, we can define the total expected cost as a join of the sequence. And in our point of view, we would like to argue that this is actually simple and also easy to calculate and also natural to kind of computing this type of property because it's simply the join of the sequence. So we hope it's intuitive. And as a main result, we show the adequacy for predicate transformer semantics. And the theorem is essentially the following. So we assume a well-typed closed program and a domain theoretic model and Eilenberg-Muir algebras and post conditions. And then we have this equality. The left-hand side is the weakest precondition we have seen, and the right-hand side is a predicate transformer semantics. And this is how it connects to the denotational computation, and this is defined more operationally. But however, the left-hand side is still a bit abstract in its definition. It's a bit less clear how it's related to the concrete transition systems or like its behavior. Therefore, we additionally show the following equality in the case-by-case manner. The property is basically the target property we want to verify is equal to the weakest precondition. So we prove this in the case-by-case manner. So the first case study is about a weighted reachability probabilities. So given a term and the post conditions, its weighted reachability probability is literally taking the weighted sum with respect to the weight, which is determined by the post conditions, and with the reachability probability. And here you can think that reachability probability is basically the terminating probability to the value v from the term m. And as a model, we employ the category of DCPOs. And the monad is the minimal sub-probability variation monad. And as an Eilenberg algebra, we define it by expectations. And as operational semantics, we can obtain a Markov chains, which is basically a label transition systems. And the state is basically the term. And also it has a designated sync state to support the terminations. And also, and the transition between these states basically the probabilistic, and the label represents the probabilities. And from the big step semantics, we can naturally define such a transition systems. And for example, if we have an algebraic operation for probabilistic branchings, we can define literally the transition probability associated with these algebraic operations. And as propositions, we show that the weighted reachability probability is equal to the weakest precondition reasoning. Therefore, it connects the operational, like very concrete definition to a more abstract definition. As a second case study, we studied a multiplicative expected cost, which has been very recently proposed. And the definition of multiplicative expected cost is very similar, but of course we have to take care, we have to consider about the cost. And here, the cost is defined by the multiplications over in the path. So this is a difference. So in the total expected cost, it's defined more like additive in the additive way, but here it's multiplicative. And as a model, we use almost same but slightly different. The category is again the category DCPO, but the monad is a minimal variation monad, but it's not a sub-probability. It's more like unbounded variations. And as an Eilenberg algebra, we can use almost same, like we can just take the expectation. But now the domain is unbounded. And then operational semantics is again almost same. It's again a Markov chain, but now we have to take care of the cost. And therefore we have a label for the cost in the transition systems. But the definitions are almost same. Like if it incurs a cost, it just remember what the cost is. And as a propositions, we show that the multiplicative expected cost defined on this Markov chain is equal to the weakest preconditions. And as a conclusion, we provide an operational view of the client-UNO's approach. Although their denotation semantics supports continuous distributions, but we leave the support for continuous distributions as future work. Also, very recently, there is an approach about index-graded monad for dependent effect systems. And as a future work, we would like to provide an operational semantics in a unified manner and prove its adequacy. That's it. Thank you for listening.
Questions? So one thought came to mind at the end. Is this work mechanized? And if not, do you have any thoughts on how you might go about doing that?
That's a very good question. Actually, we didn't, and we would like to do, but I think it's a bit, in my opinion, it's currently a bit hard to support domain theoretic feature. Like we have an unbounded recursion, and in my understanding, it's a bit subtle, like currently. So it's a, I think, good future direction.
Okay, so maybe a good challenge for the community.
Yeah, I think so.
Exact continuous distributions, are you planning to do some sort of like tape kind of stuff? It's like you have this much fuel you can burn.
Sorry, could you say it
like,
again?
For representing like continuous distributions for, I guess, real numbers, I guess you need like some exact real number representation. You need some sort of like how much fuel my program is going to run for this precision. Are you like how are you planning to support continuous distributions?
I'm not sure whether I understand your question correctly, sorry, but basically there's a, for example, lines of work by them, which is actually, they developed their theory on the category of DCPO, and we are wondering whether actually we can, like at certain point, until a certain level, probably we can rely on their framework, and there might be some new challenge, but my current view is first to take a look at their approach in more detail and see how it looks like.
Thank you.
Okay, let's thank the speaker. Now, I know it's only Thursday, but this is the final talk of ICFP.
Okay.
Okay, looks like we're good to go.
Yep.
The stage is yours.
Thank you. Hello, everyone. My name is Cesar Andrich, and today I will talk about securely extracting F-star programs with I/O to like how to extract them. This is joint work with many amazing people. Abigail is also here, so if you have any questions after the talk, you can ask both of us. So in a tool like F-star, so F-star is a proof-oriented language in which one can write a program like a web server, and it can verify that it satisfies some property, for example, that the web server doesn't leak some private key. And F-star gives us a strong guarantee that this property is satisfied. So the question is, like, after verifying the code in F-star, we have to extract it to a mainstream language to run it. And the question is if this extracted program satisfies the same property pi. And there are many reasons to think this is not the case. And if we look at what happens in practice, is that usually the extracted code gets mixed into bigger unverified code bases. And one big example of this is Evercrypt. Evercrypt is a cryptographic provider that is written in F-star and extracted to C that gets integrated in Mozilla Firefox, Linux kernel, and other tools. And this creates many problems, right? So first, extraction itself is trusted. So this means that it can introduce bugs. And the unverified code is trusted, which means that it can break the internal invariants of the verified code, especially if it's malicious or compromised. So this creates unsoundness and security vulnerabilities. And yeah, we want to fix this. So how do we want to fix it? We want to prove some criteria about our extraction. First, we would like to prove compiler correctness. If we prove that our verified code satisfies some property pi, we want to show that after extraction, this property is still satisfied. And we also want to, this is a bug. We want to prove secure compilation, or secure compilation criterion. So if we start from a verified piece of code and we extract it, and we link this with some arbitrary unverified code, and this produces some trace T, we want to show that exists a piece of F-star code that we can link with the original program so that it produces the same trace T. Right? So the intuition is that if anything that's possible after extraction was also possible in F-star, and if, for example, there is an attack here, it means that our specification in the source was already problematic, right? So this criterion is actually stronger than full abstraction because it preserves observational equivalence, but it also preserves non-interference and trace properties. And actually, we do more. We also prove the other direction, which this criterion is known as robust relational hyperproperty preservation, which is the strongest criterion of Abate et al. So in this work, we present an extraction framework with formal secure compilation guarantees for F-star programs that have I/O. So it's verified to be correct, that it's secure. The criteria are vertically composable, so if this gets extended in the future, this doesn't have to be verified. And the framework itself is written and verified in F-star. So how does this work? So we have a program written in F-star. We can see that it takes as argument a library. This will be our unverified piece of code. And it's in the IO monad. So this is a shell-embedded program using the IO monad. And basically, it's a very simple program. It just reads something from the input. It passes that to the library, to the unverified library, and then it writes the message. And we are going to verify this by using trace-producing semantics. So for each IO operation, we associate an event. So for read, we have every read that will contain the message read. For the library, we'll leave some empty space. And then for write, we'll have another event. So basically, to do extraction, we want to take this program and build syntax. And we would like to do this in F-star. So what we want is to produce a deep embedding, basically, that looks like this. And this deeply embedded program should produce the same trace, right? So now we know how our source looks like, how our target looks like. We have a shell embedding, a deep embedding. How do we define extraction? The problem is that to close this gap between these two, we have to use a meta program, which makes extraction to be a meta program. And extraction will actually use quotation. And this makes it very challenging to verify extraction itself, because it will involve verifying quotation, which is an open challenge in all proof assistance. So related work on this topic uses actually translation validation, which is also what we use. So what related work does is that it has this meta program that does two things. First, it produces the deeply embedded program, but it also produces a proof of equivalence. So why is this translation validation? Oh, sorry. It produces also proof of equivalence. So why is this translation validation? Is because these have to be type checked to be trusted that they are correct. Type checking that can fail. So in our work, we also use translation validation, but we introduce a new technique that is kind of cool. It's a new translation. We call it relational quotation. It's a new translation validation technique for quoting shell-embedded programs using typing relations. So from the shell embedding, we have a much simpler meta program compared to related work that produces a typing derivation. But what's interesting here is that when F-star type checks this derivation, it type checks that it corresponds to the original program. Because this typing relation is actually indexed by the program. So how does that look like? So basically, we define a typing relation that carves out the subset we want to extract. But instead of being indexed by a syntactic type and a syntactic value, it's indexed by a F-star type and F-star value. So it has a typing environment, F-star type, and this is an F-star value. Obviously, if we have things of type A, we cannot have in that expression free variables. So we represent such expressions by having functions from evaluations environments to expressions of type A. And basically, the variables or the free variables are variables that have values in the evaluation environment. And then if we look at the typing rules, they resemble typing rules, normal typing rules. Here it's for the return false. We can type false as bool. Again, this is F-star false and F-star bool. For variables, is given a typing environment and given a variable that exists in the typing environment. We can type from the evaluation environment the value stored in the evaluation environment for that variable, the type in the typing environment. And for the lambda is what one expects, given a body type to type B in a typing environment extended with A, we can type the arrow A to B by basically taking the argument and pushing it in the evaluation environment. So this resembles a typing relation, but it also resembles a construction introduced in deep or shallow embeddings. So first insight will be that deep or shallow embeddings are some form of typing relations. We extended on that by showing that we can also support monads, and especially diamonad, by following the typing rules of fine-grained call by value, which is basically we have two typing relations mutually recursively defined. So the second insight about this typing relation is that it is dependently typed, which gives us a huge advantage, because F-star can infer most of it. So we only have to spell out the outside typing environment, and then some of the subterms that involves the relation itself. But the rest can be inferred by F-star, and this simplifies the meta program a lot. So if we look at an example, for the example we had before, the meta program just follows the program structure and produces this typing relation, typing derivation, right? Where everything that is missing is inferred by F-star. So I said on the previous slide that these are inferred by F-star, but we actually, what we want is to spell them out so that we can refer to our program. So what happens here is that F-star will infer a type on a program, and it will have to unify them with our program that we wanted to quotate initially. And F-star can do this, and it creates a syntactic match between the two. So back to extraction, how do we use relational quotation to do extraction? So basically, we organize extraction into two steps. Relational quotation is the first step. And then from the typing derivation, it's actually pretty simple to do extraction to generate the syntax we want. It's basically, we call it a syntax generation function because it's so simple. But this is a normal F-star function that we can verify once and for all. And since our typing derivation connects the derivation to the SHAL embedded program, we can relate directly the SHAL embedding program with the deep embedding. And we use two logical relations to obtain compiler correctness and secure extraction. And the two logical relations are for the two directions of the criterion, not for, they're not, we don't need two relations for two different criterions. So in this paper, I showed you a secure compilation framework for a secure extraction framework for I/O programs. In the paper, we actually have support for refinement types. I didn't have time today to talk about it. It's a bit more complicated. We'll require also extending the typing relation with index for a precondition that one has to prove. And as future work, we would like to do more effects, work on KKML and relational compilation, show that this should be possible. They have similar techniques, but this will involve more fancier proofs that will become pretty complicated. Already the logical relations are more than half of the artifact. And targeting existing verified compilers for ML, we actually extract to Lambda box, but that step is unverified. And I'm looking for remote jobs in software verification, so if you have any hints, ping me. Thank you.
Okay, I see Sam is coming up possibly for an announcement, but Everyone else is welcome to come up for questions.
Very cool work. So I wonder if you're going to migrate this technique to another theorem program like ROC, how much would be applied there and how much work would be required?
Right, so except the refinement types that are specific to F-star, everything should be portable to any dependently typed language. Oh, yeah. So, yeah.
All right, thank you.
So I know in CompCert, translation validation was used for certain optimizations to show that those were correct. Do you think you could use a similar technique to what you've done here to minimize the use of translation validation for compiler optimizations?
But isn't CompCert fully deeply embedded and using deep embeddings? I'm not that familiar to know if one can optimize those.
Yeah, and it could very well be a bad question. Okay, let's thank the speaker.
So this concludes the program of ICFP. I want to thank Manuel again for setting up the fantastic program that we've had, but we also have 2 more great days of workshops.